welcome to the deep dive. Today, we're going to be diving into a paper that tackles like a really fundamental question in geometric measure theory.
Yeah.
It's how well can we approximate these kind of abstract objects called integral cycles using smooth submanifolds.
Right.
We're looking at optimal smooth approximation of integral cycles by Almgren, Browder, Caldini, and Lellis. It's a mouthful.
Yeah, that's a great paper.
It is a great paper.
It's a question that has roots going all the way back to Plateau's problem.
Oh, yeah, for sure.
Finding that surface of minimal area that spans a given boundary.
Right.
Integral currents provided a powerful way to kind of generalize that. But the inherent smoothness of those minimal surfaces is something that mathematicians have been poking at for ages.
Right, because integral cycles can be pretty wild, geometrically speaking.
Oh, yeah.
So what's the headline result here? Do we get perfectly smooth representations, or are there limits?
There are definitely limits,
Yeah.
and that's what makes this paper so interesting. The authors prove that you can find a smooth submanifold.
Okay.
That's a great approximation in terms of volume up to a certain codimension, but they also show why in some cases you're stuck with a bit of unavoidable roughness.
Okay, so let's unpack this carefully.
Yeah.
On page 2, they start with that historical link to Plateau's problem and how integral currents fit in.
Right.
I think for our listeners, it'd be helpful to have like a quick reminder of what integral currents actually are.
Yeah, good point.
Before we get too deep into the weeds.
Yeah, imagine you have like a curve or a surface or even some higher dimensional shape.
Right.
But it's not necessarily smooth.
Okay.
It could have kinks or sharp corners or even tears.
Gotcha.
An integral current is a way to represent that shape, including its orientation, using a kind of generalized integration.
So it captures not just the shape itself, but how it's situated in space, right? Like a circle versus a figure 8 would have different orientation.
Yes, exactly. And crucially, integral currents allow for these non-smooth aspects, which is what makes them perfect for studying things like Plateau's problem, where the solution might not be perfectly smooth.
Okay.
And that leads us to the two big questions the authors pose at the bottom of page 2 and top of page 3.
Right. The first one being, can you always find a smooth submanifold that perfectly represents the same stuff as an integral current? And it sounds like the answer is a resounding no.
It is. And the reason why it goes back to some really deep work by René Thom. He showed that there are certain homology classes that can never be represented by a smooth submanifold.
Really?
No matter how hard you try.
Wow.
There are fundamental topological obstructions.
Okay.
They mention that at the top of page 3.
So even before getting into their specific theorem, we already know there are hard limits to how smooth these approximations can get.
Exactly.
Which makes their main result, theorem 1.1 on page 3, all the more impressive. This is the optimal smooth approximation theorem, right?
Exactly. What it says is, given an integral cycle in some manifold, you can find a smooth submanifold that's a close approximation. It'll have almost the same volume, and importantly, it'll be homologous to the original cycle.
Meaning it carries the same topological information, even if the exact geometric shape is different.
Precisely.
Okay.
But the key here is how well you can approximate depends on whether a smooth representative for that homology class even exists. If it doesn't, you're stuck with some inherent roughness.
And they even quantify this, right?
They do.
Remark 1.2 on the same page says their result is optimal.
Yeah.
Meaning codimension 5 is as good as it gets in general.
Right.
I'm already curious about why that number pops up.
Yeah.
But I guess we'll get there later.
We will, and it's one of the most fascinating parts of the paper.
Okay, good. I'm looking forward to that.
But first, I think it's worth highlighting some of the implications of this theorem, because it's not just a theoretical curiosity.
Yeah, pages 4 through 6 lay out some pretty impactful consequences.
They do.
Theorem 1.5, for example, talks about the absence of Lavrentiev gaps for the homological plateau problem.
Right.
What does that even mean?
It's a mouthful.
It is.
But essentially, it means that when you're trying to minimize area, you don't lose anything by considering all integral cycles instead of restricting yourself to just the smooth ones.
Okay.
The minimal area will be the same.
That's pretty powerful.
It is.
So smoothness isn't a constraint in that context.
Right.
They also mention being able to approximate integral cycles with ones that have predefined singularity sets.
Yeah.
Theorem 1.7.
Right, which ties into some deep stuff about cohomology operations.
Okay.
And when you can actually represent homology classes smoothly, they bring up Thom's criterion and Steenrod powers, which are tools for detecting these topological obstructions.
Okay, so we've got the main theorem and some of its impact. But how do they actually prove this thing?
It's a great question.
Pages 6 and 7 give a high-level overview.
Yeah.
And it sounds pretty intricate.
It is, but it's also beautifully structured.
Okay.
They start by approximating the integral cycle near the skeleton of a triangulation of the manifold.
Okay.
It's like building a scaffold around the shape.
Okay.
Then they use this really cool tool called the Thom construction, which translates the problem into the language of homotopy theory.
Exactly. They exploit a key equivalence between Thom spaces and Eilenberg-MacLane spaces.
Yes.
Which are kind of like building blocks in homotopy theory.
Right.
And finally, they use techniques from geometric measure theory to smoothly deform that initial approximation.
It's amazing.
It's like they're taking this rough shape, mapping it into a different world where they have more flexibility to manipulate it, and then bringing it back all smoothed out. I'm already impressed. We haven't even gotten into the details yet.
Oh, the details are where the real fun begins. Shall we start unpacking those?
Let's do it. On page 11, we encounter proposition 2.1 and corollary 2.2.
Okay.
What role do these play in the grand scheme of the proof?
These are tools from homotopy theory that allow you to transfer smooth representatives between spaces.
Okay.
Remember how they map the cycle into a different space?
Right.
These propositions ensure that if you can find a smooth representative in that new space, you can bring it back to your original manifold while preserving smoothness.
So they're like smoothness translators across different mathematical worlds.
Exactly.
Now we delve into the heavy hitters, the Thom isomorphism theorem, spanning pages 13 to 15.
Oh, yeah.
This one sounds particularly important.
It is. This theorem's like a bridge between the geometry of bundles and the topology of spaces.
Okay.
It says that the cohomology of a space is closely related to the cohomology of its associated Thom space, which captures information about the way vector bundles twist over the space. Essentially, it lets you translate between geometric and topological properties.
So in this context, it helps connect the smooth structure of our manifold to the topological properties of the cycle we're trying to approximate.
Exactly. It's a key ingredient in allowing them to use homotopy theory to manipulate the cycle in a way that preserves its essential topological features.
And then there's the Thom construction itself, outlined in theorems 2.5 and 2.6.
Right.
You mentioned it earlier as a way to represent homology classes with maps, right?
Yes, the Thom construction is a brilliant method for turning a homology class into a map.
Okay.
Imagine you have a submanifold representing that class. The Thom construction essentially thickens that submanifold into a tubular neighborhood and creates a map that collapses everything outside that neighborhood to a single point.
Okay.
This map encodes the homology class in a way that's amenable to manipulation using homotopy theory.
So it's like taking a spotlight and shining it directly on the submanifold.
That's a great analogy.
While everything else fades into the background.
That's a perfect analogy. And in the paper, they extend this concept to manifolds with boundaries.
Okay.
Which is important for their proof because they're working with manifolds that might have edges or corners.
Gotcha. Okay. So far, so good. Let's move on to pages 15 through 20, where we encounter lemmas 3.1, 3.2, 3.3, and 3.4.
Right.
These seem to be laying the groundwork for the main event.
They are. These lemmas are all about carefully constructing special neighborhoods and maps around the scaleta of the triangulation we talked about earlier.
Right.
They achieve this delicate balance between maintaining control over the geometry of these neighborhoods while ensuring they're topologically equivalent to simply spaces.
Okay.
It's like creating a series of carefully crafted lenses that allow them to zoom in on specific parts of the cycle and manipulate them without distorting the overall picture.
It sounds like they're setting up a very precise and controlled environment.
They are.
For the smoothing operation. And then we get to the heart of the technical machinery. The two key propositions from geometric measure theory.
Right.
Propositions 4.1 and 4.3.
Right.
Discussed on pages 20 to 30.
Okay.
These are the workhorses of the proof.
They are. Proposition 4.1, introduced on page 20, gives them a way to create that initial approximation of the integral cycle.
Okay.
That's smooth outside of a small neighborhood of the M2 skeleton.
Right, so it's smooth in most places.
Yeah.
But they still need to deal with those potentially rough spots near the skeleton.
Exactly.
Yeah.
And that's where proposition 4.3 comes in.
Okay.
It provides a method for taking two integral cycles that agree outside of a small neighborhood of the M2 skeleton and smoothly deforming one into the other.
So they can use it to smooth out the remaining wrinkles near the skeleton while keeping everything else intact.
Precisely. And critically, this deformation process is carefully controlled to ensure that the deformed cycle stays close to the original one in terms of both volume and a measure called the flat norm, which quantifies how much one current can be deformed into another.
It sounds like a very delicate balancing act.
It is. They're essentially navigating a tightrope between achieving smoothness and preserving the essential properties of the original cycle. Shall we delve into the specifics of how these propositions work in practice?
Absolutely. Let's start with proposition 4.1. They mentioned something called deformation along normals on pages 22 and 23. What's that all about?
Imagine you have a point on the cycle near the M2 skeleton.
Okay.
At that point, you can choose a direction that's perpendicular to the skeleton, called a normal direction.
Okay.
Deformation along normals essentially means pushing the cycle a small amount.
Okay.
In that normal direction.
So it's like inflating the cycle slightly, but only in very specific directions.
That's a good way to visualize it. And they do this in a way that ensures that the deformed current is smooth in the region where the deformation happens. It's like ironing out a wrinkle, but very carefully, so you don't create any new ones.
Okay, that makes sense. But how do they control the volume and the flat norm during this deformation process?
Right.
How do they ensure the approximation doesn't become too large or deviate too far from the original cycle?
That's where their clever use of the area formula comes in. This formula relates the volume of a submanifold to the mass of the current it represents by applying the area formula to the deformed cycle.
Okay.
They can carefully estimate its volume and ensure it doesn't exceed the volume of the original cycle by more than a specified amount.
Gotcha.
They outline the details of this estimation on pages 24 and 25.
Okay.
And to control the flat norm, they use the homotopy formula, which measures how much a current changes under a continuous deformation.
So they're using these geometric and topological tools to keep the deformation process under tight control.
Exactly.
It's like they're sculpting the cycle with a very steady hand.
It is.
Ensuring every movement is precise and intentional.
It is.
What about proposition 4.3? How do they smooth out the remaining non-smooth parts near the M2 skeleton?
That's where they bring in the heavy artillery of the Thom construction, the Thom isomorphism theorem, and some delicate homotopy theory arguments, as described on pages 26 through 30. Remember how the Thom construction allows them to represent the homology class of the cycle as a map?
Right, it's like shining a spotlight on the submanifold.
Exactly. And once they have this map, they can use homotopy theory to manipulate it. They exploit a key equivalence between Thom spaces and Eilenberg-MacLane spaces, which allows them to translate the problem of finding a smooth representative for the homology class into the language of homotopy theory.
So they're transforming a geometric problem into a topological one where they have more powerful tools at their disposal.
That's a great way to put it. And the Thom isomorphism theorem is crucial here because it allows them to relate the smooth structure of the manifold to the topological properties of the cycle. It's like a dictionary that translates between the language of geometry and the language of topology.
It's amazing how they're weaving together these seemingly disparate areas of mathematics to create such a sophisticated and powerful proof.
It really is a testament to the interconnectedness of mathematical ideas.
Yeah, it really is.
They then use this homotopy theory framework to construct a smooth deformation of the original cycle. Carefully choosing the parameters to ensure the final smoothed cycle remains close to the original one in terms of both volume and the flat norm.
It's like they're carefully massaging the cycle, smoothing out the rough spots while preserving its overall shape and character.
That's a perfect analogy.
But there's one thing I'm still a bit puzzled about. How do they guarantee that the smoothing process doesn't introduce any new singularities or tiers in the cycle?
That's a great question.
Wouldn't that defeat the whole purpose?
That's a key point, and they address it very carefully. The magic lies in how they apply proposition 4.3. They carefully construct the deformation process to ensure that it only affects the cycle in a controlled region near the M2 skeleton, as detailed on pages 31 and 32. This region is already known to contain singularities.
Okay.
So the smoothing process doesn't introduce any new ones.
Gotcha.
They essentially contain the smoothing operation to the region where singularities are already present,
right,
preventing them from spreading to other parts of the cycle.
So they're working with the existing singularities, smoothing them out without disrupting the smooth structure of the rest of the cycle.
Exactly.
That's incredibly clever.
It is. And to avoid creating any tears or discontinuities, they rely on the properties of the homotopy formula, which guarantees that the deformed cycle remains a continuous object.
Okay, that makes sense. They've managed to smooth out the rough edges while preserving the essential integrity of the cycle.
Yeah.
We've covered a lot of ground already.
Yeah.
Maybe it's a good place to pause and pick up the rest of this fascinating proof next time.
Sounds like a plan. The way they bring all these pieces together is really quite elegant.
Can't wait to dive back in.
Looking forward to it. Picking up where we left off, let's recall those two propositions from geometric measure theory that form the backbone of the proof.
Okay.
Proposition 4.1 and 4.3.
Right.
They are the real workhorses in this whole smoothing process.
Right. We talked about how proposition 4.1 gives us an initial approximation that's smooth almost everywhere.
Yeah.
Except for potentially near the M2 skeleton of our triangulation.
Exactly.
It sets the stage for the finer smoothing to come.
Exactly. And proposition 4.3 is the tool that lets them take that initial approximation and iron out those remaining wrinkles, smoothly deforming it into a submanifold that truly represents the homology class.
But it's not just any old deformation, right?
Right.
They need to ensure the smoothing process doesn't introduce any new singularities or wildly change the volume of the cycle.
Right.
It's like a delicate surgery.
It is. And the way they achieve this level of precision is by cleverly combining those geometric measure theory techniques with the Thom construction and homotopy theory.
Okay. Remind me again how the Thom construction fits into all of this.
Sure.
It's been a few pages since we discussed it.
The Thom construction allows us to represent the homology class of our integral cycle as a map from the manifold to a special space called a Thom space.
Okay.
Think of it as creating a kind of topological fingerprint of the cycle.
So instead of dealing directly with the geometry of the cycle,
they're
working with a map that encodes its topological essence.
Exactly. And this is where homotopy theory comes in.
Okay.
It gives us the tools to manipulate that map, essentially deforming it in a controlled way, which in turn translates back to a smooth deformation of the original cycle.
That's pretty clever. So they're leveraging the flexibility of homotopy theory to achieve a level of control over the smoothing process that would be difficult to achieve.
Exactly.
Directly in the geometric setting.
Precisely. Now, let's zoom in on how they actually use propositions 4.1 and 4.3.
Okay.
Recall that proposition 4.1 employs this technique called deformation along normals.
Right. It's like inflating the cycle slightly, but only in very specific directions.
Yeah.
That are perpendicular to the M2 skeleton.
Exactly. On page 22 and 23.
Okay.
They describe how this deformation is carried out using a carefully constructed family of vector fields.
Okay.
These vector fields essentially provide a blueprint for how each point on the cycle should be moved.
Okay, so it's very organized and systematic
Yes.
deformation process.
It is.
But how do they ensure that the deformation doesn't create any new singularities?
Right.
Or cause the volume to explode?
That's where their meticulous use of the area formula and the homotopy formula comes into play.
Okay.
Remember, the area formula relates the volume of a submanifold with the mass of the current representing it.
Yes.
On pages 24 and 25, they apply this formula to carefully estimate the volume of the deformed cycle and ensure it doesn't exceed the volume of the original cycle by more than a predetermined amount.
So they're essentially using the area formula as a volume control knob.
That's a great way to put it.
Making sure the deformation stays within certain bounds.
Exactly. And the homotopy formula, which measures how much a current changes under a continuous deformation, allows them to control the flat norm of the deformed cycle, ensuring it doesn't deviate too far from the original one.
Okay, so they've got a good handle on the volume and the overall shape of the deformed cycle.
Right.
But what about proposition 4.3? How does that help smooth out those remaining rough spots near the M2 skeleton?
Proposition 4.3, described on pages 26 through 30, takes over once we have that initial approximation from proposition 4.1.
Okay.
It leverages the Thom construction and homotopy theory in a very elegant way.
I'm all ears.
Remember how we said the Thom construction allows us to represent the homology class as a map? Well, what Proposition 4.3 essentially does is provide a method for smoothly deforming that map.
Okay.
Which in turn translates back to a smooth deformation of the original cycle. And they do this by exploiting a key equivalence between Thom spaces and Eilenberg-MacLane spaces, which are special spaces in homotopy theory that are much easier to work with.
So they're using the Thom construction to bridge the gap between the geometry of the cycle and the world of homotopy theory.
Yes.
And then they're using the properties of Eilenberg-MacLane spaces to create a smooth deformation that wouldn't be possible to construct directly in the geometric setting.
That's a perfect summary. It's like they're using a secret passage to move between different mathematical realms.
Yeah.
Choosing the best tools from each realm to achieve their goal.
I'm starting to see how these pieces fit together.
Good.
But how do they actually guarantee that this homotopy theory magic translates back into a smooth deformation of the cycle that doesn't create any new singularities or rips in the fabric of the original object?
Yeah. That's where their meticulous attention to detail shines through.
Okay.
They carefully construct the homotopy, which is essentially a continuous family of maps, ensuring that it only affects the cycle in a controlled region near the M2 skeleton, as explained on pages 31 and 32.
Great.
This region by construction is already known to contain singularities, so the smoothing process doesn't introduce any new ones.
So they've cleverly contained the smoothing operation to a region where singularities are already present.
Exactly.
Preventing them from spreading to other parts of the cycle.
Exactly.
It's like they're quarantining the wrinkles.
That's a great analogy. And to avoid creating any tears or discontinuities during the deformation, they rely on the properties of the homotopy formula, which guarantees that the deformed cycle remains a continuous object.
Okay, so they've managed to smooth out the rough spots without introducing any new problems.
Yes.
That's quite impressive.
It is. And remember, all of this is done while carefully controlling the volume and the flat norm, ensuring that the final smooth submanifold is a faithful approximation of the original integral cycle.
We've covered a lot of ground here.
We have.
But I feel like we're starting to get a real sense of the elegance and intricacy of this proof.
We are. And the way they bring all these pieces together in the final steps is really quite beautiful.
I can't wait to see how it all comes together. Let's dive into the final stretch of the proof in our next segment.
Looking forward to it.
All right, we're back, ready to wrap up this incredible proof.
Yeah, it's a good one.
We've seen how they use propositions 4.1 and 4.3 to create this smooth approximation of an integral cycle. Carefully controlling that volume and flat norm along the way. But there's one more crucial piece to the puzzle, right?
Yes.
They need to show that their result is like the best possible, meaning you can't generally get any smoother approximations than what they've already achieved.
Exactly. It's not enough to just find a solution. They want to prove that it's optimal.
And they do this by showing that there are fundamental limits to smoothness in certain situations, no matter how clever you are with your approximations.
And that's where Thom's example comes in, right?
Exactly.
The one we've been teasing throughout this whole discussion. It's on pages 37 to 39 of the paper.
That's right.
Yeah.
Thom's example is like a counterexample.
Okay.
Showing that there are cases where you were just stuck with some degree of roughness, no matter how hard you try and smooth things out.
Okay, let's dive into the details.
Yeah.
What exactly is Thom's example? And how does it demonstrate this inherent limitation on smoothness?
So Thom's example, which they present as example 6.1 on page 37, involves a specific 7-dimensional homology class in a 14-dimensional manifold. And what Thom showed and what the authors highlight here is that this particular homology class cannot be represented by a smooth submanifold.
Really?
There's a fundamental topological obstruction that prevents it. So no matter how you try to embed a 7-dimensional shape into this 14-dimensional space, to represent that homology class, you'll always end up with some kind of singularity, some point where it's not perfectly smooth.
Precisely. And they point out that this obstruction is related to a specific cohomology operation mod 3. It's getting into some deep algebraic topology here. But essentially what it means is there's a kind of twist in the topology of this homology class that prevents it from being smoothed out.
Okay, I'm willing to trust you on the algebraic topology.
All right, good.
So we have this example where smoothness is fundamentally impossible.
Right.
But how does that prove that the result is optimal.
Okay.
How does it connect to that codimension 5 limit?
That's where their connection to the broader theory of manifolds with singularities comes in.
Okay.
Which they discuss on page 38.
Okay.
They argue that the specific type of singularity that prevents smoothing in Tom's example is not just a fluke, it's a fundamental feature.
Okay. Of certain homology classes.
So this particular example is like the tip of the iceberg, hinting at a deeper phenomenon.
Exactly.
Related to the unavoidable presence of singularities.
Exactly. They connect this to the concept of innately singular homology classes.
Okay.
Which are classes that, by their very nature, just cannot be represented smoothly.
Okay.
And because these singularities can't be removed without changing the topology of the manifold, they impose a limit on how smooth any approximation can be.
Okay, that makes sense. But why codimension 5? Why is that the magic number?
That's where things get even more interesting.
Okay.
They delve into a deep analysis of these singularities and their connection to complex projective spaces.
Okay.
Which they lay out on page 39.
Those are some pretty sophisticated objects.
They are.
Remind me what they are again.
Sure. A complex projective space is a space you get by taking a complex vector space.
Okay.
Removing the origin, and then identifying points that lie on the same complex line.
They have a very rich geometry and topology, and they pop up all over mathematics.
Right. I remember hearing about them in algebraic geometry and topology courses.
Yeah.
But how do they relate to the singularities in our problem?
The authors draw on Tom's earlier work on resolving singularity, which involves understanding the cobordism properties of the links of these singularities. Cobordism, in simple terms, is about classifying manifolds based on whether or not they can be the boundary of a higher dimensional manifold.
So it's like asking if you can fill in a manifold.
That's a good way to think about it.
To create a solid object without any holes.
Yeah, that's a good way to think about it.
Okay.
And what Tom showed is that understanding the cobordism properties of the links of singularities can help you understand the singularities themselves. The authors apply this idea to the singularities that pop up in Tom's example and discover that they're intimately connected to the cobordism properties of certain complex projective spaces.
Okay, so we have this link between singularities, complex projective spaces, and cobordism.
Yes.
But I still don't see how it all leads to codimension 5.
The key is that certain complex projective spaces are unable to bound higher dimensional manifolds.
Okay.
This inability to bound, combined with Tom's work on cobordism and singularities, implies the existence of those unavoidable singularities in certain homology classes.
Okay.
And it turns out that the dimensions of these complex projective spaces and the way they relate to cobordism lead directly to the conclusion that codimension 5 is the best possible general result.
Wow. So it's like the topological properties of these complex projective spaces are dictating the limits of smoothness in our original problem.
Exactly.
It's incredible how all these seemingly unrelated areas of mathematics all come together.
It is, and that's what makes this paper so remarkable.
Yeah, it really is.
It not only proves a powerful theorem about smooth approximations, but also reveals deep connections between geometry, topology, and even algebraic topology. It highlights the inherent unity of mathematics and how seemingly abstract concepts can have profound implications for understanding the structure of geometric objects.
Well, I think it's safe to say we've thoroughly explored this paper.
I think so.
We've delved into the intricate world of integral cycles, smooth approximations, and the inherent limits of smoothness.
Right.
Uncovering just a treasure trove of mathematical connections.
We did.
Along the way.
It's been a fantastic journey.
It really has. And we hope you, our listeners, have enjoyed this deep dive as well.
Yes.
From those historical roots in Plateau's problem to that really elegant interplay of geometry and topology.
Absolutely.
This paper truly showcases the beauty and the power of mathematical thought.
It does.
We'll be back next time with another fascinating deep dive into the world of mathematics.
Looking forward to it.
Until then, keep exploring. All right, today we're going deep on a paper called Optimal Smooth Approximation of Integral Cycles.
Ooh, yeah.
Have you had a chance to look at this one?
I have. It's quite a fascinating paper.
It is. It's tackling kind of a head scratcher.
Yeah.
How closely can we approximate an integral current using a smooth submanifold?
Yeah.
Particularly when, the current might have singularities because of topological obstructions.
Yeah, it's a classic problem, the kind of thing that keeps mathematicians up at night.
Totally. And this paper presents a theorem that gives us a surprisingly concrete answer, I think.
Yeah, it's really quite elegant, the way they managed to bridge this gap between these two worlds.
Yeah, and they set the scene so well in the introduction by going back to Federer and Fleming's work on integral currents.
Right.
And their solution to the oriented Plateau problem.
Yeah, the classic Plateau problem, finding a generalized surface of the smallest area that can span a given boundary.
Exactly.
It's such a fundamental problem, and their work was really groundbreaking.
It was
showing that every homology class with integer coefficients can be represented by a cycle of least area.
Yeah.
It's foundational.
So this paper builds on that foundation, right? And it kind of goes a step further to address the question of just how smooth these integral currents can actually be.
Exactly. They delve into the deformation theorem and the strong approximation theorem by polyhedral chains with integer coefficients, all building up to their main result, the optimal smooth approximation theorem.
I love how they frame it with two key questions. So first, how closely can one approximate an integral current representing a given homology class by a smooth submanifold?
Right.
Second, suppose that a given homology class is realizable by a smooth submanifold. Is it always possible to approximate any integral current representing that homology class by smooth submanifolds?
They really get to the heart of the matter, don't they? Capturing that inherent challenge of smoothing out those potentially jagged edges of integral currents while staying true to the underlying topology.
Okay, so to the theorem itself. Now, I have to admit, when I first read it, my eyes kind of glazed over a little bit.
Oh, yeah.
Can you break it down for us?
Of course. Of course. So at its core, the optimal smooth approximation theorem says that any integral cycle T in an oriented Riemannian manifold M can be approximated in flat norm by an integral cycle in the same homology class, which is a smooth submanifold sigma.
Okay.
And here's the kicker. This approximation has a singular set of codimension 5.
Codimension 5.
Codimension 5.
What's significant about that?
Well, that's one of the most remarkable parts of this theorem. They go on to show later in the paper that there are homology classes that just can't be represented by a smooth submanifold without a singularity of at least codimension 5.
Wow.
So this theorem isn't just giving us a solution, it's telling us the absolute limit of what's possible.
That's the best we can do.
The best we can do.
I'm starting to see why this is a big deal.
Okay.
But there's more to the theorem. It also gives some pretty specific properties of this submanifold sigma.
Oh yeah, you're right, there's more. Firstly, the theorem guarantees that the m-dimensional volume of sigma doesn't exceed the mass of T by more than some tiny predetermined amount epsilon.
Okay.
You can think of it as saying that our smooth approximation is nearly as space efficient as the original integral current.
So we're not adding a lot of extra material to smooth things out.
Exactly. Secondly, it tells us that J sigma k is an integral cycle homologous to T, and there's a specific bound on the mass of the connecting integral current S.
Gotcha.
That connection makes sure that the two cycles are homologous.
So it's all very elegant, but are those specific conditions in the theorem, right? It says we need a connected, smooth, closed, oriented Riemannian manifold M of dimension m plus n,
right,
a fixed positive epsilon.
Yes.
A non-zero element tau of the m-dimensional integral homology group.
Let's see. And an integral cycle T and M representing tau.
Yeah, those conditions define our playground.
Okay.
The Riemannian manifold gives us a space where we can measure distances and talk about curvature.
The dimension m plus n sets the stage for our cycles and submanifolds.
Okay.
Epsilon, as we've discussed, controls how close our smooth approximation needs to be. And finally, working within a specific homology class means our original cycle and its smooth counterpart are fundamentally linked topologically.
So all these elements work together to create this framework where the theorem can give us such a powerful result.
Yeah.
But I have to admit, when I first read through the proof, it felt like a whirlwind tour of really advanced mathematical concepts.
Yeah. It can be a bit daunting.
Where do we even begin to unpack this thing?
Well, it's a beautiful blend of ideas from geometric measure theory, algebraic topology, homotopy theory.
Okay.
A good starting point is to look at those key sections of the paper.
Okay.
We've got notation and preliminary results, triangulations, scalita, neighborhoods, and maps, and tools from geometric measure theory.
Okay.
Each section kind of lays out the groundwork for the final proof.
So notation and preliminary results, what's going on there?
Well, it sets up the mathematical language and tools that we'll be using throughout the proof.
Okay.
It dives into the theory of integral currents, defining concepts like the mass of a current, the boundary of a current, and the push-forward operation, which lets us move a current along a map. It's like defining the rules of the game before we start playing.
So making sure everyone's on the same page.
Exactly. And then we move on to triangulations, scalita, neighborhoods, and maps. This is where things start to get geometrically interesting.
Ooh, tell me more about this geometric playground.
Essentially, we're creating a framework for analyzing our manifold. Triangulations are a way to divide the manifold into simpler building blocks, like triangles in 2D or tetrahedra in 3D.
Gotcha.
Scalita are collections of these building blocks based on their dimension, giving us a way to organize the structure of our manifold. And neighborhoods provide a way to zoom in on specific areas of interest.
So it's like creating a map of our manifold.
Yeah.
Highlighting different levels of detail.
Exactly.
And giving us tools to navigate it.
That's a great way to put it.
Okay. And then we have tools from geometric measure theory. Probably the most intimidating section.
It sounds intimidating, but this is where we meet the real workhorses of the proof proposition 4.1 and proposition 4.3.
Right, unpack those propositions for us.
All right, so proposition 4.1 gives us a way to get an initial approximation of our integral cycle using a special type of polyhedral current.
Okay.
Think of it as a rough draft of our smooth approximation.
Okay.
It also gives us control over the mass and location of this approximation, making sure it's not too far off from the original current.
So we start with this kind of blocky approximation. Yeah. We can refine it later.
Precisely.
Yeah.
Then proposition 4.3 comes in and provides a way to smooth out that rough draft.
Okay.
Creating a final smooth submanifold that's homologous to the original cycle and has that crucial codimension 5 singular set.
It's a two-step process, opposite then smooth.
Exactly. And the paper goes on to provide really detailed proofs of these propositions using some sophisticated techniques from geometric measure theory. These proofs are where things can get really technical. But the core idea is to carefully control the process of smoothing out singularities while maintaining the key properties of our approximation.
I'm ready to dive into those proofs. But I think it's time we move on to part 2 of our deep dive.
Sounds good.
We've laid some good groundwork. Exploring the background, the main questions, the statement of the theorem, and the key tools that will be used in the proof. Now let's see how all these pieces come together to create this elegant solution to the problem of optimal smooth approximation.
Let's do it.
Okay, so let's pick up where we left off and untangle this proof of the optimal smooth approximation theorem. It really blends these ideas from different areas of math.
It does. It starts by applying proposition 4.1 to our integral cycle T.
Right.
You get that initial approximation in the form of a polyhedral cycle.
Right, which is homologous to T, has controlled mass and flat norm, and is smooth outside a neighborhood of the M2-dimensional skeleton.
That's the one. And we call that cycle S. The next stage takes us deep into topology land. We're focusing on a specific region of our manifold M, the complement of a well-chosen neighborhood of the M5-dimensional skeleton. We'll call it Q. What's real cool about Q is that it's homotopy equivalent to a complex of dimension, n plus 4.
Okay, hold on. Let's remind ourselves what homotopy equivalence means in this context.
Sure. Essentially, a homotopy equivalence tells us that two spaces are topologically the same, meaning we can continuously deform one into the other without any tearing or gluing. So our region Q, even though it might look geometrically complex, it's basically the same as a simpler n plus 4 dimensional complex from a topological viewpoint.
Okay, so we've simplified the topology of Q. But how does that help us get to that smooth approximation?
Well, this is where Tom's work comes in. He found this really crucial link between the existence of smooth representatives for a homology class and the existence of a map from our manifold into this special space called the Tom space of the universal-oriented n-plane bundle.
Tom space.
Yeah.
It's a term that sends shivers down the spines of many math students.
Right. It sounds scary. But the Tom space denoted is a topological space that captures the essence of oriented n-plane bundles. Imagine attaching an n-dimensional vector space to every point in a space. That's essentially what an n-plane bundle is.
Okay.
And the Tom space gives us a blueprint for all those bundles.
So the Tom space is a way to study these bundles in this more general abstract setting.
Yeah.
But how does it relate to our smooth approximation problem?
Thom's theorem states that a homology class can be represented by a smooth submanifold if and only if there's a map from our manifold into the Thom space that pulls back a special element called the Thom class to the Poincaré dual of our homology class.
Poincaré dual, can we make that a bit more intuitive?
Sure. Think of the Poincaré dual as a way to translate between homology classes, which describe holes in our space, and cohomology classes, which describe how you can wrap things around those holes.
Okay.
It's looking at the same topological information, but from different perspectives.
So Thom's theorem tells us we can find that smooth submanifold if we can find a map that aligns the topology of our manifold with the topology of the Thom space in a specific way.
Precisely. Like finding a perfect match between these two seemingly different worlds. And that's exactly what the proof sets out to do next. Remember our region Q?
Yeah.
We said it's homotopy equivalent to an n+4 dimensional complex. Well, there's a key result from homotopy theory that says there's a map, we'll call it H, from the Thom space to a space called the Eilenberg-MacLane space, KZN.
Eilenberg-MacLane space. Another one that might send listeners running for their topology textbooks.
I know. It might sound intimidating, but the Eilenberg-MacLane space is a really handy tool. It's like a dictionary that translates between topological information in the form of homotopy classes of maps and algebraic information in the form of cohomology groups. And our map H acts as the translator, linking the geometry of the Thom space to the algebra of cohomology.
So H bridges the gap between those two different ways of describing topological information.
Right. And we use H to construct another map F from our region Q into the Thom space. This map F is carefully designed so that when we translate everything into cohomology using H, it agrees with the Poincaré dual of our homology class.
Okay.
In essence, F is encoding the topological information we need to guarantee the existence of a smooth approximation.
So we're using all these tools from different areas of math to create this smooth submanifold.
Exactly. And F is the key to the next step. We use it along with some clever smoothing techniques to construct a smooth submanifold N within Q that represents the same homology class as our original cycle T.
So we've got this smooth submanifold that matches T, at least within Q. But what about the rest of the manifold?
Great question. Our smooth submanifold N currently only lives in Q. Remember, that's the complement of a neighborhood of the M five-dimensional skeleton. So the next step is to carefully extend N to cover the whole manifold M except for that M five-dimensional skeleton. This gives us a new smooth submanifold. We'll call it sigma prime.
So we've patched up our smooth approximation to cover almost everything. But we still have that singular set.
We do. Sigma prime is homologous to T, but it has a singular set of codimension 5. Remember, that's exactly what the theorem predicted. The final stage involves using proposition 4.3 to refine this approximation and make sure it checks all the boxes of the theorem.
Proposition 4.3 to the rescue again. So how does that help us in this last step?
Well, remember, proposition 4.3 gives us a way to smooth out a cycle while confining its singular set to a small neighborhood of the M2-dimensional skeleton. We apply it to our current smooth approximation sigma prime and a slightly modified version of our initial polyhedral approximation S. This gives us our final smooth submanifold R prime. It's homologous to T, has controlled mass, and a singular set of codimension 5.
It's like watching a sculptor refine their work, chipping away imperfections until they get this masterpiece. We started with a rough integral current, carefully crafted a smooth approximation, and then meticulously refined it to satisfy the theorem.
I love that analogy. The whole process shows how powerful it is to combine ideas from different parts of math. Geometric measure theory helps us create the approximations. Algebraic topology guides us in understanding the structure of the manifold and the existence of smooth representatives. And homotopy theory provides the tools to connect those abstract concepts to our concrete construction.
But we've only addressed the first part of the theorem.
Oh, right.
What about the second part, which says that if our homology class already has a smooth representative, then we can approximate any way integral cycle in that class smoothly.
Yeah, that's where things get even more interesting. The proof for the second part builds on a similar logic, but with a twist. It uses the existing smooth representative as a template to guide the construction of the smooth approximation for any other integral cycle in the same homology class.
So it's like we have a blueprint for smoothness.
Exactly. Knowing there's a smooth representative gives us a shortcut to smooth out any other integral cycle in that homology class.
It really highlights that relationship between topology and geometry. Understanding the topology gives us these powerful tools to control the geometric properties.
Absolutely.
This has been an incredible journey uncovering the optimal smooth approximation theorem and all the elegant math in its proof.
It really is a beautiful result.
But we're not quite done yet. There's still more to explore, like the implications of this theorem and the world of innately singular homology classes.
Let's do it.
All right, so let's shift gears a bit and talk about the implications of this theorem. The absence of Lavrentiev gaps theorem is really interesting to me. It seems like it has consequences for the calculus of variations.
It does. It addresses a fundamental question in the calculus of variations. Can we get the same minimal area whether we consider all integral currents or just smooth submanifolds in a homology class?
So does allowing for those rougher integral currents give us any advantage?
Right. And the absence of Lavrentiev gaps theorem says nope. It says that we achieve the same minimal area whether we're working with all integral currents or just smooth submanifolds in the same homology class, which is really useful practically speaking.
Yeah, like if you're designing a bridge or a building.
Exactly. You don't have to worry about losing efficiency by sticking to smooth surfaces.
So it's a very elegant result, showing this harmony between the smooths and the more general world of integral currents. But I know the paper also explores those cases where smooth approximations aren't possible, right?
Right. Tom's example, it demonstrates the existence of these innately singular homology classes. Homology classes that can't be represented by any smooth submanifold.
So there are some geometric barriers that we just can't smooth over.
Exactly. Tom gives this example of a 7-dimensional homology class in a 14-dimensional manifold, and it shows this fundamental obstruction to smooth approximation. And what's really interesting is that this isn't just a weird quirk of this specific example. They actually show you can construct similar obstructions in lower dimensions.
So this codimension 5 singularity in Tom's example is a fundamental limit.
Right. It's the best we can do. And the paper goes into geometric obstruction theory and cobordism groups to explain why that barrier is optimal.
It's amazing. We've explored this elegant solution to the smooth approximation problem, seen that harmony between the smooth and singular world, and then encountered these limits to smoothness in these innately singular homology classes.
It really highlights the interplay between topology and geometry.
It does. Before we wrap up, can you leave our listeners with something to think about?
Sure. Given what we know about geometric obstruction theory, what other examples of these innately singular homology classes are out there in different dimensions? What can we learn by studying those classes? And what are the implications of these inherent singularities for other areas of math, like minimal surfaces or geometric flows, even theoretical physics?
Excellent questions. I think our listeners have plenty to ponder. Thanks for guiding us through this world of smooth approximations. It's a great reminder that even in math, there are still so many mysteries to unravel. Welcome to the Deep Dive. Today, we're going to be tackling a fascinating problem.
Yeah.
From the world of geometric measure theory.
That's right.
How closely can we approximate those potentially jagged integral cycles with smooth submanifolds? We've got a dense research paper packed with theorems and proofs to unpack. But don't worry, we're here to guide you through the mathematical maze.
That's right. We'll break down the complex concepts, highlight the key insights, and explore the implications of this groundbreaking research.
So to set the stage, we're dealing with integral cycles,
right,
which can be thought of as generalized surfaces that might have edges, corners, or even more complicated singularities.
Sure.
Think of the boundary of a cell.
Right.
It's not perfectly smooth. But we can still describe its overall shape and properties using integral currents.
Exactly. And the challenge is to find a smooth submanifold that closely approximates this potentially rough integral cycle. It's like trying to fit a perfectly smooth sheet onto a crinkled surface. You might be able to get pretty close, but there might be some inherent wrinkles you just can't iron out.
And this is where the concept of codimension comes in, right? It essentially measures the difference in dimensions between the spaces involved.
Precisely. If you imagine a curve which is one-dimensional, lying on a surface which is two-dimensional, the codimension is 1.
Okay.
It's the gap in dimensions between the object and the space it's embedded in.
Okay, that makes sense. So why is finding these smooth approximations important? It seems like a pretty abstract mathematical puzzle.
It turns out that these smooth approximations are incredibly useful for a variety of reasons.
Oh, okay.
First, they allow us to apply powerful tools from differential geometry and calculus to analyze and understand the behavior of these complex shapes.
So it's like by smoothing things out, we unlock a whole new set of mathematical tools that were previously unavailable.
Exactly. Second, smooth approximations are often essential for modeling physical phenomena. In materials science, for example, the interfaces between different materials can be incredibly complex, but by approximating them with smooth submanifolds,
right,
we can model how materials will behave under stress, how they'll conduct heat, and all sorts of other important properties.
Wow, so this seemingly abstract mathematical result could have a direct impact on the design of new materials and technologies.
Absolutely. And the applications extend to fluid dynamics, where smooth approximations of vortex filaments can help us understand complex fluid flows.
All right.
And even to cosmology, where they can be used to model the large-scale structure of the universe.
I'm starting to see how this deep dive is more than just a theoretical exercise. It's about uncovering mathematical tools that have the potential to shape our understanding of the world around us.
Precisely. Now, before we dive into the details of the paper, let's take a step back and acknowledge the historical context of this problem.
Okay.
Mathematicians have been grappling with the question of how smooth integral currents truly are for decades.
So this isn't a new problem. It's been a long-standing challenge in the field.
Exactly. Even the founders of integral current theory, Federer and Fleming, noted the surprising smoothness of integral currents back in their groundbreaking 1960 paper.
Interesting. So even back then, mathematicians were intrigued by this tension between the potential roughness of integral currents and their inherent smoothness.
Absolutely. And the paper we're diving into today builds on this legacy.
Okay.
It explicitly lays out the two key questions driving this research.
Okay.
First, how closely can we approximate an arbitrary integral current with a smooth submanifold?
Okay.
And second, can we do even better if we know the homology class of the integral current is already representable by a smooth submanifold?
Okay, so they're essentially asking, what are the limits of our ability to smooth things out, and are there cases where we can achieve perfect smoothness?
Exactly, and the paper's main result, Theorem 1.1, provides a powerful and surprising answer to these questions.
Okay, I'm ready to hear about this breakthrough. What does the theorem say?
The theorem states that given any integral cycle, T representing a homology class, and any positive number, no matter how small, there exists a smooth submanifold that approximates T incredibly closely.
What does incredibly closely mean in this context?
It means two things.
Okay.
First, the volume of P is almost the same as the mass of T.
Right.
Specifically, the volume of P is no more than larger than the mass of T.
Right.
Second, opening T differ only within a codimension of 5.
Okay.
In simpler terms, they only differ in a way that's limited to 5 dimensions.
So they're almost identical in size and only differ in a very specific high-dimensional way. That's pretty impressive.
Right.
But the paper also emphasizes that this codimension of 5 is the best possible result. Right. Why is that?
That's because of those inherent topological obstructions we talked about earlier, those shapes that are fundamentally unsmoothable.
Right.
Remember Tom's example from the 1950s? He found a 7-dimensional homology class that cannot be represented by any smooth submanifold.
Right. So even though we can get incredibly close to a smooth approximation, there are some fundamental limits dictated by the topology of the shapes we're dealing with.
Exactly. And to really understand why this codimension of 5 is optimal, we need to dive into the details of the proof.
Okay.
It's a fascinating blend of geometric measure theory and algebraic topology, using a clever combination of tools and techniques to achieve this remarkable result.
Okay, I'm ready to get into the nitty-gritty of the proof. Where do we start?
The proof kicks off with the concept of triangulation.
Okay.
Which is essentially dividing the manifold into smaller, simpler pieces called simplices.
Right.
Think of it like building a complex structure out of Lego bricks.
Okay, so they're breaking down the problem into smaller, more manageable chunks.
Exactly. The next step is to approximate the integral cycle with a special type of current called a polyhedral chain.
Okay.
Imagine a polyhedral chain as a surface built from flat pieces like a 3D jigsaw puzzle.
So they're replacing the potentially curvy and complicated integral cycle with something more structured and easier to work with.
Precisely, this polyhedral chain will be close to the original integral cycle in both mass and flat norm.
Okay.
And it'll have the additional property of being smooth outside of a small neighborhood of the M2 skeleton of the triangulation.
Hold on, what's this M2 skeleton business?
Think of the M2 skeleton as the collection of all the M2 dimensional faces of the simplices in the triangulation.
Okay.
In simpler terms, it's like the scaffolding of our Lego structure, the lower dimensional framework that holds everything together.
Okay, I'm starting to visualize it. So they're approximating the integral cycle with a polyhedral chain that's smooth almost everywhere except near this scaffolding of the triangulation.
You've got it. Now, the next step is to use a tool from algebraic topology called the Tom construction.
Okay.
This allows them to relate the smooth part of the polyhedral chain to a map from the complement of a neighborhood of the M5 skeleton to the Tom space of the universal-oriented n-plane bundle.
Whoa, that sounds intense. Can you maybe break that down a bit? What's the Tom space, and why are we suddenly talking about bundles?
Think of the Tom space as a way of compactifying a vector bundle.
Okay.
A vector bundle is essentially a collection of vector spaces attached to each point of a space. It's like having a little arrow pointing in every possible direction at every point in our space.
Okay, I'm vaguely following. So they're using this Tom construction to connect the geometry of the smooth part of the polyhedral chain to something more topological.
Precisely.
Involving these bundles and planes.
Precisely. And by carefully analyzing this map, they can show that it's possible to construct a new integral cycle that's homologous to the original one, but has singularities confined to the M5 skeleton.
So they've essentially pushed the singularities into a lower dimensional space closer to that scaffolding we talked about earlier.
Yeah.
That's a big step towards smoothing things out.
It is. And finally, they use a delicate geometric measure theory argument to show that this new integral cycle can be further deformed to a smooth submanifold that's incredibly close to the original integral cycle in both mass and flat norm.
That's quite a journey. They start with a rough polyhedral approximation, use some fancy topology to push the singularities into a smaller space, and then finish with the geometric smoothing step.
You've got it. And the key is that each step in this process is carefully designed to preserve the key properties of the original integral cycle, ensuring that the final smooth approximation is a faithful representation of the original shape.
This is truly mind-bending stuff, but I'm starting to appreciate the elegance and power of their approach. It's like they found a way to tame the wildness of these complex shapes and reveal their underlying smoothness.
That's a wonderful way to put it, but the real beauty of mathematics is that these seemingly abstract results often have profound implications for our understanding of the real world, and that's what we'll explore in the next part of our deep dive.
I can't wait to see where this mathematical journey takes us next.
So far, we've journeyed through the theoretical landscape of integral cycles and smooth approximations. Now, let's shift gears and explore how this seemingly abstract mathematical result has profound implications for our understanding of the real world.
I'm eager to see how this all connects to real-world phenomena. Where do we begin?
Let's start with material science. Imagine the intricate interfaces between different materials, often filled with irregularities and complexities.
I can picture that's like the jagged boundary between two rocks or the uneven surface of a piece of fabric.
Exactly. Now, by applying the smoothing theorem, we can approximate these complex interfaces with smooth submanifolds. This opens the door to powerful analytical tools from differential geometry and calculus.
So by smoothing things out, we unlock a whole new set of mathematical tools that were previously unavailable.
Precisely, these tools allow us to model and predict how materials behave under stress, how they conduct heat, and all sorts of other crucial properties.
So this mathematical result could lead to more accurate simulations and better designs for materials used in everything from airplanes to smartphones.
Absolutely. Think about the development of lightweight, high-strength materials for aerospace applications, or the design of flexible, durable screens for electronic devices. This theorem could play a crucial role in advancing these technologies.
That's incredible. It's amazing how a seemingly abstract mathematical concept can have such a direct impact on our technological world.
And the applications don't stop there. Let's move on to fluid dynamics, where the shapes of vortex filaments, those swirling patterns you see in water or smoke, can be modeled using integral cycles.
Vortex filaments. So we're talking about the elegant spirals of a hurricane or the turbulent eddies in a river.
Precisely by applying this smoothing theorem, we can gain insights into the dynamics of these complex fluid flows.
I imagine that understanding these dynamics is crucial for a wide range of applications, from weather forecasting to designing efficient turbines.
You're absolutely right. Accurate weather predictions rely heavily on understanding the complex interplay of air currents and vortex formations. Similarly, optimizing the design of wind turbines or airplane wings depends on accurately modeling the fluid flow around these structures.
It's truly fascinating how this mathematical result bridges the gap between abstract theory and concrete applications, leading to advancements in fields that seem completely unrelated at first glance.
That's the beauty of mathematics. It provides a universal language for describing and understanding patterns and structures across diverse domains, from the microscopic world of materials to the vast scales of fluid dynamics.
I'm curious about those cases where we encounter those inherent topological obstructions, those shapes that are fundamentally unsmoothable. Does the paper address those situations?
It absolutely does. The paper acknowledges this challenge and proves a weaker version of the theorem to handle such cases.
So they don't just give up on those unsmoothable shapes.
Not at all. This weaker version states that even if a homology class cannot be represented by a perfectly smooth submanifold, we can still find an integral cycle that's smooth outside of a small neighborhood of the M2 skeleton.
Okay, so even in the most challenging cases, they can still achieve a significant level of smoothness, just not perfect smoothness everywhere.
Exactly. It's like saying that even if you can't iron out every wrinkle on a crumpled piece of paper, you can still smooth out most of it, leaving only a few stubborn creases.
And importantly, they show that this weaker result is the best we can do in general. There will always be some level of roughness that can't be completely eliminated no matter how sophisticated our mathematical tools become.
Precisely. This underscores the fundamental limits imposed by topology, highlighting the interplay between geometry and topology in shaping our mathematical understanding of the universe.
Now, after exploring the implications of the main theorem, does the paper delve into the intricacies of its proof?
It does, and it's a fascinating journey through the realms of geometric measure theory and algebraic topology.
Okay, I'm ready to get a bit technical.
Yeah.
Can you walk me through some of the key steps involved in their approach?
Absolutely. The proof begins by utilizing a powerful tool from geometric measure theory, the deformation theorem for integral currents.
Deformation theorem. That sounds intriguing. What does it entail?
Essentially, this theorem allows us to approximate any integral current, no matter how complex, by a polyhedral chain, which we've discussed earlier.
Right. The polyhedral chain is like a simplified, structured representation of the potentially curvy and intricate integral current.
Precisely. And the beauty of this deformation theorem is that it bridges the gap between the continuous world of geometric measure theory and the discrete world of algebraic topology.
Ah, so it enables them to leverage the power of algebraic topology, which is well suited for studying these structured polyhedral objects.
You got it. Now, to further simplify their analysis, they employ the notion of a Lipschitz neighborhood retract.
Lipschitz neighborhood retract, that's a mouthful. Can you unpack that for me?
Imagine you have a space embedded within a larger space. A Lipschitz neighborhood retract allows us to retract a neighborhood of that space back onto the space itself without distorting distances too much.
So it's like shrinking a puffy jacket down to its core shape without tearing or stretching it too much.
That's a great analogy, and the reason this concept is crucial is that it allows them to work with integral currents in a more abstract setting, focusing on their intrinsic properties rather than the complexities of their surrounding space.
Makes sense. It's like zooming in on the essential features of the integral current without getting bogged down in the details of its environment.
Exactly. And to connect these geometric measure theory concepts to the realm of algebraic topology, they introduce the concept of a mapping cylinder.
Mapping cylinder. Is it anything like a physical cylinder?
In a way, yes. Imagine taking a continuous map between two spaces and constructing a cylinder where one end is attached to the first space and the other end to the second space, guided by the map.
So it's like creating a bridge between two spaces using a cylinder as the connecting structure.
That's a great way to visualize it. And the reason mapping cylinders are so powerful is that they allow us to relate the homotopy types of the two spaces.
Homotopy type, is that about how spaces can be deformed into each other?
You're exactly right. It's like asking whether you can smoothly morph one shape into another without tearing or gluing the mapping cylinder provides a framework for studying these deformations and understanding the topological relationships between spaces.
I'm starting to see how they're piecing together this intricate puzzle using tools from different mathematical domains. It's like building a complex structure using Lego bricks from different sets.
That's a brilliant analogy, and by skillfully combining these tools and concepts, the authors of this paper managed to construct the smooth approximation of the integral cycle step by step.
I'm eager to hear more about the specific details of their construction, but perhaps we should save that for the next part of our deep dive.
I agree. We've covered a lot of ground already, and it's important to give our listeners time to digest these concepts in the final part of our deep dive. We'll delve into the heart of the proof, exploring the elegant interplay of geometric and topological ideas that lead to this remarkable result.
We've explored the profound implications of this smoothing theorem, venturing from that intricate world of material science to the swirling dynamics of fluid flows. Now it's time to delve into the heart of the mathematical machinery to unravel the elegant tapestry of the proof itself.
That's right. It's time to roll up our sleeves and get into the nitty-gritty details of how this remarkable result comes to life.
I'm ready for the challenge.
Yeah.
You mentioned earlier that the proof begins by focusing on the regions where the integral cycle is already smooth, using a clever triangulation strategy. Can you elaborate on that?
Absolutely. The authors begin by constructing a smooth triangulation K of the manifold M. Think of this triangulation as dividing the manifold into a network of beautifully interconnected simplices, those fundamental building blocks of geometry.
So they're breaking down the potentially complex manifold into a collection of simpler geometric shapes.
Exactly. Now, the key insight is to focus on approximating the integral cycle outside a neighborhood of the M2 skeleton of this triangulation.
Ah, yes, the M2 skeleton, that scaffolding we discussed earlier, where the simplices of lower dimensions intersect. But why focus on the regions away from this skeleton?
It's a brilliant strategic move in the regions away from the M2 skeleton. The integral cycle is already smooth, allowing them to leverage the powerful tools of differential geometry to construct a smooth approximation. The real challenge then lies in extending this smooth approximation to those trickier regions near the M2 skeleton where singularities might lurk.
So it's like a divide and conquer strategy. Smooth out the easy parts first, then tackle the more challenging regions with a targeted approach.
Precisely. And the paper meticulously guides us through the steps of this intricate process. First, they employ a technique called coning off to handle the integral cycle within a neighborhood of each M2 simplex.
Coning off? That sounds intriguing. Can you paint a picture of what that looks like?
Imagine you have a loop of string lying flat on a table. Now imagine lifting one point of that loop upwards, pulling it towards a fixed point above the table. The surface swept out by the string as it stretches and rises forms a cone.
Ah, I see it. So they're essentially replacing the potentially complicated geometry of the integral cycle near the M2 skeleton with these simpler cone-shaped structures.
Exactly. And the beauty of this approach is that these cones are smooth everywhere except at their very tips, which coincide precisely with the M2 skeleton itself.
So they've strategically pushed the singularities into an even smaller, more confined space, those pinpoints where the cone tips meet the M2 skeleton.
Precisely. Now, with the singularities neatly tucked away at the cone tips, the next challenge is to smoothly approximate the boundaries of these cones, which lie on the M1 skeleton of the triangulation.
Okay, so now they're focusing on smoothing out the edges of those cones, those boundaries that lie one dimension higher in the triangulation.
Exactly. And to achieve this, they employ a sophisticated blend of techniques from differential topology and geometric measure theory.
This is where the proof starts to get really intricate, isn't it? I can sense the mathematical gears turning.
It does. They utilize tools like tubular neighborhoods, which you can think of as creating a buffer zone around a space, and transversality arguments, which deal with how spaces intersect each other.
So they're carefully manipulating and deforming these boundaries, ensuring that the resulting submanifolds are smooth and well-behaved.
Precisely and crucially, they do this while meticulously preserving the homology class of the original boundaries.
Right, that's essential. They need to ensure that these smooth approximations don't fundamentally alter the topological character of the shapes they're working with.
Exactly. Now, with the boundaries of the cones beautifully smoothed out, the next step is to extend these smooth approximations to the cones themselves. And this is where the Tom construction makes its grand reappearance.
Yes, the Tom construction, that powerful tool from algebraic topology that you mentioned earlier. Remind me how it comes into play here.
The Tom construction allows them to relate those smooth submanifolds they've painstakingly constructed to a map from the complement of a neighborhood of the M5 skeleton to the Tom space of the universal-oriented n-plane bundle.
Okay, bear with me here. We're dealing with the complement of a neighborhood of the M5 skeleton. So essentially, everything outside of a small buffer zone around that lower dimensional scaffolding. And this is being mapped to the Tom space, which is, if I recall, a way of compactifying a vector bundle, that collection of vector spaces attached to every point in our space.
You're following it beautifully. And the key insight here is that this map, guided by the Tom construction, can be deformed into a new map that's transverse to the zero section of the bundle.
Transverse to the zero section. Can you elaborate on what that means?
Imagine the bundle as a collection of arrows attached to every point in our space. The zero section is simply the collection of all those arrows that have zero length. They're essentially just points.
Okay, so it's like identifying all the anchor points within this vast forest of arrows.
Precisely. Now, being transverse to the zero section means that our deformed map intersects this collection of anchor points in a clean way without any tangencies or overlaps.
I see. So it's like ensuring that the map cuts through those anchor points smoothly and cleanly.
Exactly. And the brilliance of this approach is that the pre-image of this zero section under the deformed map Essentially, all the points in our original space that get mapped to those anchor points gives us a smooth submanifold that approximates the original integral cycle incredibly well.
So it's like they're using the Tom construction as a guide to navigate this vast space of possibilities and pinpoint the right smooth submanifold that fulfills all the desired criteria.
That's a fantastic way to put it. And the paper goes on to demonstrate with meticulous detail how this final smooth submanifold satisfies all the desired properties in terms of volume homology class and that crucial codimension of 5.
It's truly a testament to the power of combining ideas from different mathematical realms for the continuous world of geometric measure theory to the discrete structures of algebraic topology. It's like they've woven together a tapestry of mathematical ideas to achieve this remarkable result.
You've captured it perfectly. But remember we talked earlier about those inherent topological obstructions, those shapes that are fundamentally unsmoothable. The paper addresses this challenge head-on, showing why this codimension of 5 is truly the best we can achieve in general.
Right, those pesky singularities that refuse to be completely tamed. How do they demonstrate this fundamental limit?
They revisit Tom's classic example, that 7-dimensional homology class that cannot be represented by a smooth submanifold. They show how this example can be generalized to construct integral cycles in any codimension less than 5 that simply cannot be smoothly approximated with arbitrarily small error.
So no matter how hard we try, no matter how sophisticated our mathematical tools become, there will always be some inherent roughness that we cannot eliminate. It's a fundamental limit imposed by the very nature of topology itself.
Precisely. And this highlights the profound interplay between geometry and topology, revealing how these two fields are inextricably linked in shaping our understanding of the mathematical universe.
Well, I think we've reached the bottom of this particular deep dive. It's been an incredible journey from the abstract world of integral cycles and smooth approximations to the concrete applications in material science and fluid dynamics, culminating in this elegant and powerful proof.
It's been a privilege to guide you through this mathematical landscape, to unravel the intricate beauty and surprising connections that lie at the heart of this groundbreaking research.
And for you, dear listener, I hope this deep dive has sparked your curiosity and ignited a sense of wonder about the power of mathematics to illuminate the hidden patterns and structures that shape our world. Welcome to the deep dive. You ready to get into some serious math today?
Oh, absolutely. Always up for a challenge.
Today's source material is a real treat.
Oh, yeah.
Optimal smooth approximation of integral cycles. It's by Almgren, Browder, Caldini, and Lellis.
Now, that's a paper that really brings together some beautiful math.
It does. Geometric measure theory, topology, and calculus of variations. We're going to be all over the place today. In a good way, of course.
I'm excited to dive in.
So what we're trying to understand is how we can approximate those integral cycles, those potentially really complex ones,
right,
with smooth submanifolds, while still keeping their essential properties, topologically speaking.
Kind of like smoothing out a wrinkled surface, but without changing its fundamental shapes.
A perfect analogy. Okay, so the abstract jumps right in, page 1, the core finding. We can do this. Approximate integral cycles using these smooth submanifolds, but there's a catch. A singular set of codimension 5.
And that codimension 5 is super important. It's not random at all. The paper actually proves it's the best we can do, generally speaking.
Oh, so there's like a hard limit.
Exactly.
Interesting. They even mentioned Tom's example here. We'll get to that.
Oh, yes, Tom's example, a classic.
She goes that sometimes these singularities just won't budge, like no matter how hard you try.
Like trying to perfectly flatten a crumpled piece of paper, some creases will always remain.
Exactly. Okay, let's move to the introduction. Pages 2 and 3. They start with the work of Federer and Fleming.
That sets the stage.
Their 1960 paper, The Oriented Plateau Problem, a game changer. It basically asked, can you always find a surface, like the absolute minimum area, that spans a given boundary?
And they proved that you can, but the solution might have some kinks. Singularities, where the surface misbehaves, let's say.
So not always a smooth surface then. Fascinating. Which brings us to the big questions this paper tries to answer. How closely can we approximate an integral current using a smooth submanifold, especially when we're talking about minimizing area?
That's a big one.
And if we can represent a homology class.
A way to group equivalent cycles, right?
Yeah. If we can represent one with a smooth submanifold, does that automatically mean we could approximate any integral current in that class using smooth submanifolds?
Million-dollar questions. And the authors tackle them head-on with Theorem 1.1, the optimal smooth approximation theorem, pages 3 and 4.
Okay, this theorem has 3 parts to it. So part 1, for any integral cycle T, and this represents a homology class in a manifold M. Got it.
You're following along?
You can find a smooth submanifold, and it's a good approximation of T. What's cool is that the volume of T doesn't get much bigger than the mass of T. We're keeping things tight.
Efficiency is key.
Right. The second part gets into the topology, the relationship between I and T. So it says the current associated with I is homologous to T, connected by an m+1 dimensional current.
Making sure they're topologically linked, so to speak.
Exactly.
Yeah.
And the third part, well, that focuses on those special cases, where the homology class itself is represented by a smooth submanifold. No kinks.
The best case scenario.
In these cases, I can be totally smooth. No singular points whatsoever.
And this is where remark 1.2 comes in on page 4. A little reminder. This codimension 5 result. The best we can hope for, generally. Tom's example is going to show us why. Eventually.
Okay, I'm intrigued. Let's keep going. Pages 4 through 7. We encounter Theorem 1.5, which tackles this idea of Lavrentiev gaps. Can you break this down for us?
Sure. Think of a functional like the area functional. Lavrentiev gap happens when the infimum of that functional is different, depending on whether you're considering all admissible objects or just the smooth ones.
Like the minimal area changes depending on if we allow kinks or not.
Exactly. But thankfully, Theorem 1.5 tells us we don't have to worry about that here. The minimal area stays the same, whether we allow singularities or not.
So no need to stress about missing out on the optimal solution, just because we want things to be smooth.
Precisely.
Excellent. Now, remark 1.6 on page 7 highlights those special situations where all homology classes can actually be represented by smooth submanifolds.
Yes. This happens when the codimension n is 1 or 2, or when the dimension of the cycles m is 1, 2, 3, 4, 5, or 6. In these lower dimensions, Theorem 1.1 is even stronger. We're guaranteed a smooth submanifold, homologous to any integral current, no singularities needed.
Wow. So as we move into those higher dimensions, things get more complex.
Yeah.
And those unavoidable singularities start popping up.
It's like a whole new world of challenges.
Exactly. And the authors provide a glimpse into why this happens. They mentioned that smooth representability for a homology class is linked to the vanishing of specific cohomology operations. Things like Steenrod squares and box-beam homomorphisms. They're like detectors, revealing obstructions to smoothability.
So if these operations don't vanish, we know we're dealing with a homology class that just can't be represented by a perfectly smooth object.
Like a red flag. No smooth allowed here.
Exactly. Now, on pages 6 and 7, they give us a high-level view of their proof strategy for Theorem 1.1. It's a beautiful blend of geometric measure theory and topology, working together to construct those smooth approximations.
A true mathematical masterpiece. Now let's delve into the technical foundation. Pages 8 through 15, we start with section 2.1, integral currents.
This section lays the groundwork, defines the objects we're trying to approximate. They introduce concepts like the mass, support, and push forward of a current, all essential for measuring and manipulating these generalized surfaces.
Right, and they talk about integer rectifiable currents. I imagine those as surfaces built from countable pieces. And then there's integral currents, which are those integer rectifiable currents, but with an additional condition on their boundaries.
Don't forget the flat norm. It gives us a way to measure the distance between two currents.
And that takes into account both their geometric shape and their boundaries.
Precisely.
Okay. So we've got our integral currents defined. Now, in section 2.2, it's a whirlwind tour of homotopy theory and cobordism.
Setting the stage for understanding those unavoidable singularities. And, of course, for constructing the smooth approximations. They bring in Eilenberg-MacLane spaces, which are essentially spaces that embody cohomology groups. And then there's Thom spaces, constructed from vector bundles. They play a critical role in connecting smooth submanifolds to homology classes.
It's like building a bridge between different mathematical worlds.
Exactly. They also remind us about the powerful Thom isomorphism theorem, which connects the cohomology of the base space of a vector bundle to the cohomology of its Thom space.
Okay, I see the pieces starting to come together here. Now, on pages 15 through 20, they bring in triangulations and neighborhoods of Scalita. Specifically, the concept of suitable neighborhoods in section 3.1.
This is where the geometric and topological aspects start to really intertwine. They want to work with neighborhoods of the Scalita, You can think of them as the backbones of the triangulations. And these neighborhoods need to have certain properties.
So they introduce these neighborhoods, booba sub, k sub sub, and visa sub, key sub, where key sub sub represents a j-dimensional skeleton. The key point is that these neighborhoods need smooth boundaries and deformation retracts onto the scaleta.
And that's where lemmas 3.1 and 3.2 come in. They ensure that these neighborhoods have well-behaved boundaries and smooth tubular neighborhoods.
They're really setting the stage carefully here, making sure they can work with objects that are, well, smooth enough for their topological tools.
Precisely. Now, pages 20 to 31, we're getting to the heart of the geometric measure theory arguments, propositions 4.1 and 4.3.
Proposition 4.1 focuses on constructing an initial approximation of the integral current, T. They want to find another integral cycle, denoted P, which is homologous to T, doesn't have too much extra mass, and is smooth outside a small neighborhood of the M2 skeleton.
It's like a first draft, a good starting point.
Exactly. And they break down the construction of P into two steps. First, they regularize the current on the complement of the M1 skeleton, essentially pushing the current away from those lower dimensional cells to get smoothness.
Smoothing things out step by step.
Right. And in step 2, they carefully remove the remaining M1 dimensional singularities, while staying away from a small neighborhood of the M2 skeleton. It's a delicate balancing act.
A lot of intricate steps involved.
And lemma 4.7 is a key player here. It allows them to smoothly lift the current away from those M1 dimensional faces.
Clever use of tools.
Okay, so they've created this initial approximation, P high, which is smooth outside a neighborhood of the M2 skeleton. In proposition 4.3, they shift gears. Now, they want to deform this approximation to get even closer to the original integral current T.
Refinement time.
Exactly. And here's the key insight. If two integral cycles are the same outside a small enough neighborhood of the M2 skeleton, guess what? They actually represent the same homology class. And you can smoothly deform one cycle to be close to the other, both in terms of mass and the flat norm.
Amazing how these seemingly small details can have such profound implications.
It is. To prove this, they cleverly use lemma 3.3, which helps construct diffeomorphisms. And these diffeomorphisms are isotopic to the identity and behave well near the scaleta.
Like a mathematical compass guiding the deformation process.
Exactly. And they also use lemma 4.8 to estimate the mass of that deformed cycle, making sure that deformation doesn't add too much extra area.
Keeping things under control.
Okay, that brings us to pages 31 through 37, where we finally reach the peak. The proof of theorem 1.1.
It's the culmination of everything. Integral currents, triangulations, neighborhoods, Thom spaces, homotopy theory. It's a mathematical symphony.
I love it. So how do they actually orchestrate this proof? What are the key movements, so to speak?
Well, they start with the approximation P, remember? The one from proposition 4.1, smooth outside a neighborhood of the M2 skeleton, homologous to T, and its mass isn't too much bigger than that of T.
Right. A solid starting point, but of course they want to refine it even further.
Of course. The goal is to use P to construct a new cycle, but this time smooth outside an even smaller set, the M5 skeleton. And here's where they bring in the heavy machinery, Thom's construction.
Yes, Thom's construction. Could you remind me the essence of that again?
Sure. It essentially provides a powerful connection between smooth submanifolds and homology classes. And it does this by using maps into Thom spaces. Remember those vector bundles and Thom spaces from earlier? Well, Thom's construction basically says this. You can represent a homology class by a smooth submanifold if, and only if, you can find a map from your manifold into the Thom space of a specific universal bundle. And this map has to pull back the Thom class to the Poincare dual of your homology class.
Okay, that's a lot to digest, but I think I'm starting to see the connection. We've got this homology class represented by our integral current, and we're searching for a smooth submanifold that represents the same class. So we need to build this special map into a Thom space.
Exactly, and that's precisely what they do. First, they look at the complement of a carefully chosen neighborhood of the M2 skeleton, denoted as A. They choose this neighborhood so that its boundary is smooth and a deformation retracts onto the M2 skeleton.
So careful attention to detail here, making sure they can apply those topological tools smoothly.
Always. Now, because our approximation P is smooth outside a neighborhood of the M2 skeleton, it defines a smooth submanifold within A.
Because A excludes that troublesome neighborhood where P might have singularities, right? Yeah.
Right. And using the smooth submanifold, they construct a map from A into the Tom space of the universal-oriented n-plane bundle. And they designed this map so that it pulls back the Tom class to the Poincare dual of our homology class, but restricted to A.
So it's like applying Tom's construction locally within the specific subset A?
Precisely. Now, they want to expand this to the entire manifold. So they consider the complement of a neighborhood of the M5 skeleton denoted as Q, and thanks to lemma 5.1, Q has the homotopy type of an n+4 dimensional skeleton. They then leverage this fact. The Tom space of the universal n-plane bundle is n+4, equivalent to an Eilenberg-MacLane space KZ and M. This space, remember, captures the nth cohomology group with integer coefficients.
Okay, so they're using this equivalence to transfer information about the homology class from A to Q.
Exactly. This equivalence, together with proposition 2.1, allows them to show that the restriction of the Poincare dual of our homology class to Q, well, it can be represented by a map from Q into the Tom space.
So now they've got a map from Q into the Tom space, representing the homology class, just like they had a map from A into the Tom space.
Precisely. And again, they make sure this map is smooth and transverse to the zero section of the bundle. This guarantees that its preimage is a smooth submanifold, representing the homology class restricted to Q.
So two smooth submanifolds, one in A, one in Q, both representing the same homology class. What happens next?
Well, they notice something interesting. A is actually inside Q. And because of lemma 5.1, A has the homotopy type of an n+1 dimensional complex. Using this, and corollary 2.2, they show that the two maps, the one from A and the one from Q into the Tom space, well, they're homotopic when restricted to A. This means the two smooth submanifolds they found are essentially the same, up to homotopy, in their overlapping regions.
So they kind of glued together those two smooth submanifolds in A and U, creating a new one defined on a bigger part of the manifold.
Exactly. Now, using lemma 3.4, they extend this smooth submanifold to the entire manifold, and the result, an integral cycle that's smooth outside the M skeleton and homologous to our original integral current, T.
They did it. They constructed the smooth approximation.
Yes, but wait, there's more. They still need to prove that this approximation meets all the conditions of theorem 1.1, show that its mass isn't much bigger than that of T, and that it's close to T in terms of the flat norm.
Okay, how do they handle that part?
They rely on proposition 4.3. Remember, it says that if you've got two integral cycles, and they're the same outside a small neighborhood of the M2 skeleton, then there is a smooth deformation of one cycle that gets really close to the other, both in mass and flat norm.
So they apply this proposition to their new smooth approximation and the original integral current, T.
Exactly. And by carefully choosing the parameters, they make sure that the deformed cycle checks all the boxes of theorem 1.1.
Wow. Such intricate work. It seems like they've successfully proven theorem 1.1, showing that we can approximate any integral cycle with a smooth submanifold, with a singular set of codimension 5, and if the homology class itself can be represented by a smooth submanifold, no singularities at all.
That's the beauty of it. Now, in section 6, they shift gears a bit. They delve into Tom's example, a remarkable discovery that proves this codimension 5 result is the best we can do. In general,
Tom's example, they've hinted at it throughout the paper. What is it exactly?
It's a specific homology class, 7-dimensional, within a 14-dimensional manifold. And no matter how hard we try, we can't represent it with a smooth submanifold.
So it's like a worst-case scenario, showing that the codimension 5 result is optimal.
Exactly. In example 6.1, they describe it in detail. They start with lens spaces. These are created by taking a sphere and identifying points related by a cyclic group action.
Twisted spheres with interesting topological property.
Got
it.
Exactly. Now, Tom's example is constructed by taking the product of two 7-dimensional lens spaces, which gives you a 14-dimensional manifold. Then, they very carefully pick a 7-dimensional homology class in this manifold, specifically designed so that it can't be represented by a smooth submanifold.
And they use cohomology operations to show this.
Right. A cohomology operation called a Steenrod square shows that this homology class has a non-vanishing obstruction to smoothability.
It's like a detector, flagging the impossibility of a smooth representation.
Precisely. And remark 6.2 points out something interesting. While Tom's homology class itself can't be represented by a smooth submanifold, a multiple of it can.
Oh, so there's a loophole.
It means the obstruction is a torsion element. It disappears when you multiply it by the right integer.
So even if we can't completely eliminate singularities, sometimes we can tame them by looking at multiples of the homology class.
Exactly. Now, after example 6.1, they discuss the geometric side of Tom's example, why this particular homology class is inherently singular.
They mention it represents a codimension 5 non-removable singularity. What does that mean exactly?
It means you can represent this homology class by a cycle with a two-dimensional set of singularities. But if you try to deform the cycle to remove them, you'll inevitably increase their dimension.
It's like hitting a wall at codimension 5. We can push singularities down to codimension 5, but no further.
Exactly. And they explain that this non-removable singularity is closely tied to the fact that the complex projective plane, CP2, doesn't bound a 5-dimensional manifold.
Okay, getting deep into topology here. But I'm starting to appreciate the bigger picture. These unavoidable singularities come from fundamental topological roadblocks.
Precisely. And then they discuss Tom's work on geometric obstruction theory, a framework for understanding and classifying singularities.
Right, they mentioned that each singular simplex in a triangulated space has a link, which is a manifold that describes the local topology around the singularity. How do these links help us resolve singularities?
Well, according to Tom's obstruction theory, we can resolve a singularity using a blow-up if its link bounds a compact manifold.
So it's like cutting out the singularity and stitching in a smooth patch.
Exactly. And the obstruction to resolving the singularity is measured by a cohomology class in a cobordism group. Cobordism, remember, classifies manifolds based on whether they bound higher dimensional manifolds. If the link of a singularity is null cobordant, meaning it bounds a higher dimensional manifold, then the singularity can be resolved. If not, it's inherently there to stay.
So links in cobordism groups help us figure out if a singularity can be smoothed out or not. Fascinating.
In Tom's example, the link of that two-dimensional singularity is the complex projective plane, CP2, which, as we said, is not null cobordant. That's why the singularity in Tom's example is unavoidable.
Makes sense. So Tom's obstruction theory helps explain why that codimension 5 result in theorem 1.1 is the best we can do. Fundamental topological limitations prevent us from completely getting rid of singularities in higher codimensions.
Exactly, and they formalize this in theorem 6.3.
So theorem 6.3 basically says, forget about finding a smooth approximation with a singular set of codimension 6 or higher for Tom's homology class. Not going to happen.
Precisely. They prove it by using Tom's obstruction theory, showing that the obstruction to resolving that two-dimensional singularity in Tom's example is non-vanishing.
A hard limit. Theorem 6.3 really highlights the interplay between geometry, topology, and analysis when studying integral currents.
It does. Now, on page 38, they discuss another interesting result, one that allows us to reduce the dimension of a cycle's singularities.
Oh, tell me more about that.
It involves this blow-up technique. You can replace singularities with smoother objects, but only if certain topological conditions are met.
What kind of conditions?
The key one is that the link of the singularity must bound a compact-oriented smooth manifold.
So if we can find a smooth manifold to fill in the boundary defined by the link, we can use this blow-up technique to smooth out the singularity.
Exactly. They even illustrate it using Tom's example, explaining how you can reduce the dimension of that two-dimensional singularity by replacing its conic fibers with compact manifolds that bound the links.
So even though we can't completely eliminate singularities in Tom's example, we can at least tame them a bit using this blow-up technique.
Precisely. A valuable tool in studying singularities in general.
This is incredible. We've gone from the basics of integral currents all the way to Tom's construction and obstruction theory, even touched on ways to simplify singularities. A whirlwind tour of some pretty complex math.
It has been, and we're not done yet. There's still more to explore in the world of optimal smooth approximation of integral cycles.
So let's pick up where we left off. Page 38. The authors are diving deeper into Tom's obstruction theory, especially that part about reducing the dimension of singularities in a cycle.
Right. They talk about this technique where if a cycle, we'll call it T, has a singularity locus, sub of dimension S, well, we might be able to smooth things out, resolve those singularities using a blow-up method. And the key, the link of each S-dimensional simplex of sub.
Okay, so these links, they're basically MS one-dimensional manifolds, giving us a peek into the local topology around each singularity. And if the link bounds a compact manifold, then we can resolve the singularity.
Exactly. Like we're performing surgery, removing the singularity and replacing it with a smooth patch. And that patch perfectly matches the boundary defined by the link. They use this notation S sub for the R-dimensional oriented cobordism group. It helps classify these manifolds based on whether they bound higher dimensional manifolds.
So we can simplify things if these links are what they call null cobordant, meaning they bound higher dimensional manifolds. And we keep going, simplifying, until we hit a link that's not null cobordant. And that's our stopping point.
You got it. It shows us how much we can smooth things out, how smoothable the homology class is.
Okay, so on page 39, they connect this back to Tom's example, emphasizing that we just can't find a smooth representative for that specific homology class.
Right, because that obstruction to resolving the singularity, it's all about the complex projective plane, CP2, which, remember, doesn't bound a compact-oriented, smooth five-dimensional manifold, so that singularity in Tom's example, it's stuck, can't smooth it out completely.
It's like CP2 being a stubborn wrinkle we just can't iron out. Because it doesn't bound a five-dimensional manifold, there's just no way to fill in that singularity with a smooth object.
A perfect analogy. And it really highlights the limitations of smooth approximation, especially as we move into higher codimensions.
Absolutely. Okay, so stepping back, we've covered so much ground. Integral currents, Tom's construction, obstruction theory, even techniques for simplifying singularities.
It's been a whirlwind tour of some really beautiful mathematics.
Yeah, so for those listening, let's summarize first. Approximating integral currents with these smooth submanifolds is a powerful tool in geometric measure theory, especially when you're trying to minimize area.
For sure. And second, the combination of geometric measure theory and topology is what makes these approximations possible. They work together beautifully.
Right. And finally, we learned that some homology classes, like Tom's example, have those inherent singularities, and they put a limit on how much smoothness we can achieve.
It's like this fascinating dance between the smooth and the singular, the continuous and the discrete.
A perfect way to put it. Well, as we wrap up our deep dive today, I'm left with a question. Knowing that this codimension 5 result is the best we can do, what does this tell us about singularities in higher dimensional objects? Are there new mathematical tools waiting to be discovered to help us tackle these challenges? Something to ponder until our next deep dive. Welcome to the deep dive. Today, we're going to be exploring some really intricate mathematical concepts. We're diving into a research paper today, and it's called Optimal Smooth Approximation of Integral Cycles.
Okay.
And the authors are Fredrick Almgren, William Browder, Gianmarco Caldini, and Camillo de Lellis. And it's this fascinating exploration of integral currents and their smooth approximations.
Yeah, and what I think is so captivating about this work is that it really dives into the relationship between these abstract, potentially irregular integral currents and the more, familiar, well-behaved world of smooth submanifolds.
Yeah.
It's like, you're trying to bridge the gap between the messy reality of like a crumpled sheet of paper and the ideal smoothness of a perfectly flat plane.
Right. So for our listeners, let's set the stage here. Imagine surfaces like a sphere or the surface of a donut. Integral currents offer a way to kind of generalize those ideas, allowing us to talk about surfaces with potentially complicated singularities, almost like wrinkles or creases that defy smoothing.
Precisely. And the key question that this paper tackles is, how closely can we approximate these integral currents using smooth submanifolds? Can we always find a smooth representation that captures the essence of the integral current without those troublesome singularities?
And the answer, surprisingly, isn't always a straightforward yes. There are inherent limitations tied to the topology of the space itself. This paper goes deep into explaining why and how these limitations arise.
Yeah, the central result of the paper is what they call the optimal smooth approximation theorem. And in essence, it states that given an integral cycle denoted as T, which represents a certain homology class, let's call it, we can find a smooth submanifold that approximates T remarkably well in terms of volume.
But here's the catch. T can be smooth almost everywhere except for a small set of points. And the paper proves that these points must have a codimension of at least 5. So it's as if we can iron out almost all the wrinkles in that crumpled sheet. But a few stubborn creases just refuse to budge.
Yeah, it's fascinating, isn't it? And the paper not only tells us about, these unavoidable creases, but it digs into the very reason for their existence. And to truly understand this, we need to kind of step back and look at the historical context of integral currents.
Right. The idea of integral currents was first introduced by Federer and Fleming back in the 1950s. And they were working on something called the oriented plateau problem. Essentially trying to find the surface with the absolute smallest area for a given boundary. Picture a soap film stretching across a wire frame, They were looking for the mathematical description of that minimal surface.
Right, and their work led to the deformation theorem and the strong approximation theorem, both of which were early attempts to understand how smooth integral currents could be. The deformation theorem, for instance, showed that any integral current can be approximated by polyhedral chains, essentially surfaces built from flat polygonal pieces, like a 3D jigsaw puzzle.
So those early theorems were like laying the groundwork, showing that some level of approximation was possible. But this paper goes further, pushing the limits of those approximations and revealing those inherent topological barriers.
Yeah, and to do that, they bring in some serious firepower from algebraic topology, particularly the concept of Thom spaces. Thom spaces are a way to translate geometric problems into topological ones. It's like shifting your perspective to see the problem in a new light, revealing hidden structures and connections.
So instead of focusing solely on the geometric shape of the surfaces, they're looking at their topological properties, essentially how those surfaces are connected and how many holes they have.
Exactly. And one of the key tools they use to connect these geometric and topological worlds is the Thom isomorphism theorem. It's like a Rosetta Stone that allows them to translate between the language of geometry and the language of topology, revealing hidden relationships between the two.
Now let's get to the heart of the matter here. The optimal smooth approximation theorem itself. It sounds incredibly technical. Can you break it down for us step by step?
Of course. So the theorem formally states, let M be a connected, smooth, closed-oriented Riemannian manifold of dimension m plus n. Let M0 be a fixed non-zero element of the m-dimensional integral homology group, AIM Z, and T be an integral cycle representing K. Then there is a smooth triangulation K of M and an oriented m-dimensional smooth submanifold S of M5, where KM5 denotes the M skeleton of K, with the following properties. 1. The m-dimensional volume of PUD does not exceed the mass of T by more than S, that is, him, mt plus m. 2. The current Jiang is an integral cycle homologous to T, and there is an integral m plus one-dimensional current S in M such that MSS equals Jiang and MS. 3. If it admits a smooth representative, then M can be chosen to be a smooth submanifold of M.
Okay, that's quite a mouthful. Let's unpack that a little bit for our listener.
Right.
First, what's a Riemannian manifold?
A Riemannian manifold is essentially a smooth space where we can measure distances and angles, much like our familiar Euclidean space. Think of it as a generalization of our usual geometric intuition to more abstract settings.
And what about this m-dimensional integral homology group? That sounds pretty intimidating.
It might sound daunting, but it's a powerful way of describing the holes in our space. The m-dimensional integral homology group, M, Z, captures all the different ways we can arrange m-dimensional cycles. Think of them as closed loops or surfaces within our space, taking into account their orientation.
So it's like classifying the different types of holes our space can have. And the mass of an integral current is a measure of its size, similar to the area of a surface.
Precisely. So the theorem is essentially saying that for any integral cycle T representing a certain homology class, we can always find a smooth submanifold A that's not much larger than T, and they both belong to the same homology class. They essentially represent the same shape in our space, just with different levels of smoothness.
And the key point is that K is smooth everywhere, except for a set of points with codimension at least 5. Now, the proof of this theorem is where things get really interesting. They utilize a clever combination of geometric measure theory and algebraic topology. Let's dive into that. How do they actually construct this smooth approximation P?
Yeah, the proof is quite intricate. It involves a series of steps. First, they construct a preliminary approximation, denoted as P, which is smooth outside of a small neighborhood of the M2 skeleton of a triangulation of M. Think of a triangulation as dividing our space M into manageable smaller pieces, like a complex 3D jigsaw puzzle. The M2 skeleton is like the scaffolding that holds these pieces together.
So P is smooth almost everywhere except for regions close to the scaffolding. What happens next?
The next ingenious step is to utilize the Thom construction. This powerful tool allows them to translate the geometric problem into a topological one, essentially mapping our space M onto a special space called the Thom space, and this map carries crucial information about the homology class of our integral cycle.
Okay, I'm starting to see the picture here. They use the Thom construction to analyze the topological properties of the integral cycle and then utilize those properties to create a smoother approximation.
You got it. By carefully examining the properties of the Thom space, they're able to construct a new integral cycle, let's call it R, which is a smooth submanifold, but with all its singularities concentrated within the M5-dimensional skeleton of M. Remember, this M5 skeleton is a smaller, more refined scaffolding than the M2 skeleton.
So they've managed to push all those pesky singularities into an even smaller, more confined region of our space. But how do they go from R to that final, smooth approximation R?
The final step is to invoke a technical result from geometric measure theory. It essentially tells us that if two integral cycles agree outside of a small neighborhood of the M2 skeleton, then we can smoothly deform one into the other. It's like gently reshaping one surface into another without tearing or creating any new holes.
So they use this deformation to carefully mold R into Ia, ensuring that it stays close to the original integral cycle T, both in terms of volume and homology class. It's a delicate balancing act, ensuring they capture the essence of the original shape while achieving the desired smoothness.
Precisely. It's a remarkable feat of mathematical construction. And remember, the authors go to great lengths to prove that this codimension 5 is the best we can achieve in general. Sometimes those singularities are simply unavoidable, an inherent part of the topology of the space itself.
Now, to really grasp the significance of this codimension 5 result, we need to venture into the realm of cobordism theory. It sounds kind of intimidating, but it's a fascinating way of classifying manifolds based on their boundaries.
Think of it like this. Two manifolds are cobordant if together they form the boundary of a higher dimensional manifold. Imagine two circles. They can be seen as the boundary of a cylinder. Cobordism theory helps us understand these relationships between manifolds and their boundaries in a much broader sense.
And how does cobordism theory relate to the optimality of codimension 5 in this case?
The authors ingeniously utilize cobordism theory to demonstrate that certain homology classes simply cannot be represented by smooth submanifolds no matter how we try to smooth them out. There are inherent obstructions that prevent us from achieving perfect smoothness in these cases.
They provide a specific example, right?
Yeah.
Something called Tom's example.
Yes. Tom's example is a classic illustration of this phenomenon. It's a 7-dimensional homology class in a 14-dimensional manifold that can only be represented by a cycle with singularities, even though the manifold itself is perfectly smooth.
So even if the space we're working in is perfectly smooth, there might still be homology classes that inherently require singularities.
Yeah.
It's a mind-bending concept.
It is, and this example plays a crucial role in establishing that codimension 5 limit in their theorem. The authors demonstrate that Tom's example essentially represents the worst-case scenario for smooth approximations. Any integral cycle can be smoothed out except for a set of singularities with a codimension of at least 5.
So Tom's example acts like a benchmark, showing us the absolute limit of how well we can smooth out integral currents. It's a fascinating interplay between geometry and topology where the very structure of space itself imposes these limitations.
Precisely. Tom's example serves as a mathematical proof of concept, demonstrating that sometimes singularities are unavoidable, regardless of our attempts to eliminate them. They're like knots in a rope that cannot be untangled without cutting the rope itself.
This raises a fundamental question. Why codimension 5? What makes this number so special? Why not 4 or 6?
The answer lies in the intricate machinery of algebraic topology, specifically in the study of cohomology operations and characteristic classes. These are powerful tools that allow us to probe the deeper structure of topological spaces, revealing hidden properties that might not be apparent at first glance.
Can you give us a glimpse into how these tools work? I imagine it's like peering into the hidden architecture of these mathematical objects.
Imagine you're exploring a dark, uncharted cave. You have a flashlight, which represents a cohomology class, eliminating certain parts of the cave. Cohomology operations are like special lenses you can attach to your flashlight, revealing hidden features that were previously invisible.
So different lenses reveal different aspects of the cave, giving us a more complete understanding of its shape and structure.
Exactly. And characteristic classes are like markers we leave behind as we explore, indicating which parts of the cave we've already visited and what we've learned about them.
Okay, I see the analogy. But how do these lenses and markers help us understand the codimension 5 limit in our context?
The authors cleverly utilize specific cohomology operations known as Steenrod squares and Pontryagin classes to analyze the homology class in Tom's example. And they discover that these operations detect an obstruction to representing this class by a smooth submanifold. Essentially, these operations reveal a fundamental roughness in the homology class that prevents it from being perfectly smoothed out.
So it's like those cohomology lenses are revealing a hidden texture to the homology class, and this texture forces the existence of singularities. And this roughness can only be smoothed out if we allow for singularities of codimension 5 or higher.
That's an excellent way to put it. It's a testament to the power of algebraic topology to provide deep insights into seemingly purely geometric problems. It's like using abstract mathematical tools to reveal hidden geometric constraints.
Now, stepping back for a moment, what are the broader implications of this theorem? What does it tell us about the relationship between integral currents and smooth submanifolds?
One of the key takeaways is that while integral currents can be incredibly complex and potentially messy, they can be remarkably well approximated by smooth submanifolds, at least up to a certain level of singularity. It's a remarkable balance between the ideal world of smooth geometry and the more realistic world of singular objects.
It's like saying that even though we can't perfectly iron out all the wrinkles in a crumpled sheet of paper, we can get pretty close to a smooth, flat surface.
Precisely. And this has important implications for various areas of mathematics, including geometric measure theory, calculus of variations, and even theoretical physics. Understanding these approximations can provide new tools and insights into a wide range of problems.
Can you give us some specific examples of how this theorem might be applied in those fields?
Certainly. One area where this result is relevant is in the study of minimal surfaces. Minimal surfaces are surfaces that minimize area subject to certain boundary conditions. They appear in various natural phenomena like soap films stretching across a wire frame or the shapes of cell membranes.
So understanding how to approximate integral currents by smooth submanifolds could potentially lead to new ways of constructing or analyzing minimal surfaces. Perhaps even influencing fields like material science or architecture, where minimal surface designs are highly sought after.
Exactly. It could provide new tools for understanding their properties and even for constructing new examples with desired properties.
Another area where this theorem could have significant implications is the study of geometric flows, like the mean curvature flow.
Yeah, mean curvature flow is a fascinating process where a surface evolves over time in a way that minimizes its area. It's like watching a soap film slowly changing shape until it reaches a stable configuration, driven by the forces of surface tension.
And how does the optimal smooth approximation theorem play a role in understanding these flows?
Understanding how to approximate singular surfaces by smooth ones could provide new insights into the singularities that arise during these geometric flows. It could help us understand how these singularities form, how they move, and how they ultimately affect the long-term behavior of the flow.
So this seemingly abstract theorem about integral currents and smooth approximations has the potential to unlock new discoveries in a wide range of mathematical and physical problems. It's a testament to the interconnectedness of mathematics and its power to illuminate diverse areas of scientific inquiry.
It is indeed. And speaking of interconnectedness, one of the things that struck me about this paper was the way the authors seamlessly weave together techniques from geometric measure theory, algebraic topology, and differential topology. They've created this rich tapestry of mathematical ideas, each thread contributing to the overall beauty and complexity of the work.
It's like they're using multiple instruments to compose a symphony of mathematical understanding, each instrument adding its own unique voice to the overall harmony.
That's a beautiful analogy. It highlights the importance of having a broad mathematical toolkit. The more tools we have at our disposal, the more equipped we are to tackle challenging problems and uncover hidden connections between seemingly disparate areas of mathematics.
This paper we've been discussing, it's not just about solving a specific problem, is it? It's about pushing the boundaries of what we know and opening up new possibilities for mathematical exploration. It's about expanding our understanding of the very nature of geometric objects and the tools we use to study them.
Precisely. And it highlights the incredible power of collaboration in mathematics. You know, this paper brought together experts in geometric measure theory, algebraic topology, and differential topology, each contributing their unique perspectives and expertise to tackle this challenging problem.
It's a reminder that some of the most significant advances in mathematics come from breaking down those disciplinary silos and embracing the power of diverse perspectives. It's about bringing together different ways of thinking, different approaches, different tools, and forging something new and powerful from that fusion of ideas.
Couldn't agree more. And speaking of diverse perspectives, one of the things that intrigued me about this paper was how the authors highlighted the limitations of smooth approximations. They didn't just focus on what can be smoothed out. They explored those cases where singularities are unavoidable, where the very topology of the space imposes inherent limitations.
It's like they're acknowledging the inherent roughness of the mathematical landscape, recognizing that not everything can be perfectly smoothed out. Sometimes those singularities, those points of irregularity, are essential features that cannot be ignored.
Exactly. And that brings us to an intriguing aspect of the paper that we haven't touched on yet, the concept of smooth representability and the Lavrentiev gap phenomenon. These concepts delve into the limitations of representing certain mathematical objects using smooth, well-behaved functions or surfaces.
So it's like asking, when can we find a smooth, continuous representation of a given object? And when are we forced to deal with those unavoidable points of discontinuity or singularity?
Precisely. And the paper subtly hints that the Lavrentiev gap phenomenon, which we'll explain in a moment, doesn't occur in this specific problem of approximating integral currents. This adds another layer of intrigue to the whole discussion.
Okay, let's unpack this. What exactly is this Lavrentiev gap phenomenon, and why is it relevant to our discussion?
To understand the Lavrentiev gap phenomenon, we need to first touch upon the concept of smooth representability. In essence, not all homology classes, remember those ways of classifying shapes based on their holes, can be represented by a perfectly smooth submanifold. Sometimes the best we can do is get close, as the theorem showed us, but those pesky singularities might persist.
So even if we're working within a perfectly smooth space, like a sphere, we might encounter homology classes that are inherently rough, requiring those singularities to fully represent them.
Exactly. And the Lavrentiev gap phenomenon pops up in the context of the homological plateau problem. Remember, the classic plateau problem asks us to find a surface with the smallest possible area bounded by a given curve. The homological plateau problem generalizes this, asking us to find the smallest surface within a specific homology class.
So instead of finding the smallest surface bounded by a specific curve, we're searching for the smallest surface that belongs to a particular category of shapes, defined by its homology class. We're adding another layer of constraint to the problem.
Precisely. And the Lavrentiev gap phenomenon tells us that sometimes the smallest rough surface, one with singularities, can actually have a smaller area than the absolute smallest smooth surface within the same homology class. It's a counterintuitive result, suggesting that sometimes those singularities can actually help us achieve a more efficient solution.
That's mind-bending. It's like saying a crumpled piece of paper can sometimes take up less space than a perfectly flat one. So even though we can approximate those rough surfaces with smooth ones, those approximations might miss out on crucial geometric properties or fail to capture the true minimal solution.
Exactly. And the fact that this paper suggests the absence of the Lavrentiev gap phenomenon in this particular problem adds another layer of depth to the results. It tells us that in this specific context, those smooth approximations are not only possible, but also don't sacrifice the essential geometric properties of the integral current they're approximating.
This deep dive has been an incredible journey so far, revealing the intricate world of integral currents, their smooth approximations, and the limits of smoothness itself. But before we wrap up, I'm curious about the broader implications of this research. Where does this all lead? What new horizons does this work open up?
Well, for one, it significantly deepens our understanding of the relationship between smooth and singular geometric objects. This knowledge has implications for various fields, including minimal surface theory, where understanding these approximations could lead to new ways of constructing or analyzing minimal surfaces, potentially influencing fields like material science or architecture.
And what about the techniques themselves? This powerful blend of geometric measure theory and algebraic topology, do they have applications beyond this specific problem? Do they offer new ways of thinking about other mathematical challenges?
Absolutely. The use of Thom spaces and cobordism theory to understand the limitations of smooth approximations is a powerful approach with potential applications in other areas of geometry and topology. It could even inspire new ways of thinking about singularities in entirely different fields of mathematics or even physics.
So this paper isn't just a solution to a specific problem. It's a launchpad for new ideas and explorations. It's a testament to the power of mathematical thinking to uncover hidden connections and push the boundaries of human understanding. Who knows what new mathematical landscapes await us just beyond the horizon of our current knowledge?
It's a humbling thought, isn't it? That there might be entire mathematical universes hidden within these singularities just waiting to be explored. This idea that the very fabric of these mathematical objects might conceal incredible complexities we haven't even begun to grasp.
Speaking of complexity, we haven't even touched upon the concept of resolution of singularities, which is hinted at in the source material. Can you shed some light on that?
Ah, yes. Resolution of singularities is a fascinating and challenging area of mathematics. It essentially asks, can we always find a way to smooth out singularities in a more general sense? Can we find a way to transform a singular variety into a smooth one, perhaps by modifying it in a controlled way?
So it's like taking a crumpled object and finding a way to carefully unfold it, smoothing out those creases and wrinkles without tearing or changing its fundamental essence.
Exactly. And it's a problem that has deep connections to algebraic geometry, where singularities often arise naturally in the study of algebraic varieties.
But it's not just about smoothing things out, is it? It's about understanding the nature of those singularities, their structure, and how they relate to the overall geometry of the object.
You hit the nail on the head. Resolution of singularities is not just about making things smoother, it's about understanding the geometric information encoded in those singularities. It's about recognizing that those singularities often carry crucial information about the object itself.
So it's like those singularities are not just imperfections, they're essential features that tell us something fundamental about the object's geometry and topology.
Precisely. And one of the fascinating aspects of resolution of singularities is that it often involves constructing a new space, a resolution of the original space, where the singularities are replaced by smooth, well-behaved structures.
So it's like building a new, improved version of the original space, one where those troublesome singularities are tamed and controlled, but the essential geometric information is preserved.
Exactly. And the techniques used to achieve this are often quite sophisticated, drawing upon tools from algebraic geometry, topology, and even differential geometry.
It sounds like an incredibly challenging area of research, pushing the boundaries of our understanding of geometric objects and the tools we use to study them.
It is, and one of the intriguing connections highlighted in this paper is the link between geometric singularities and the algebraic obstructions arising from cobordism groups. Remember those cobordism groups we discussed earlier, classifying manifolds based on their boundaries?
Yes. Those are fascinating. So you're saying there's a relationship between those abstract algebraic structures and the very concrete geometric phenomenon of singularities.
Precisely. The paper hints at a deep connection between the obstructions to finding smooth representatives for homology classes, which are encoded in those cobordism groups, and the geometric singularities that prevent us from achieving perfect smoothness.
So it's like those algebraic obstructions are reflecting, in a very abstract way, the geometric reality of those singularities. It's like those algebraic structures are aware of the geometric limitations imposed by the singularities.
It's a remarkable interplay between algebra and geometry, where abstract algebraic concepts are intricately linked to concrete geometric phenomena. And this connection raises further questions. Can we use these algebraic tools to predict the types of singularities that might arise in a given geometric setting? Can we develop new algebraic techniques to classify and understand those singularities in a more systematic way?
It seems like this paper opens up a whole new avenue of research, exploring the deep connections between algebra, topology, and geometry in the context of singularities. It's like shining a light on a hidden landscape, revealing new structures and relationships waiting to be explored.
It is. And it's a reminder that even in a field as seemingly well-established as geometry, there are still profound mysteries to be uncovered, new connections to be made, and new frontiers to be explored.
This has been an incredibly insightful deep dive, uncovering the intricate world of integral currents, smooth approximations, and the limitations of smoothness itself. But before we conclude this episode, I'd like to leave our listener with a final thought-provoking question.
I'm all ears.
If singularities are not merely imperfections, but rather essential features of geometric objects encoding valuable information about their structure and topology, could it be that our very pursuit of perfect smoothness is limiting our understanding of the geometric world? Could it be that by trying to eliminate these singularities, we're actually discarding valuable information and potentially missing out on a deeper understanding of the true nature of geometric objects?
That's a profound question, and one that mathematicians continue to grapple with. It challenges us to reconsider our assumptions about what constitutes good or desirable geometry. Perhaps those singularities, those points of apparent imperfection, are precisely where the most interesting and profound geometric insights lie hidden.
It's like we're shifting our perspective, moving away from this classical notion of, perfection in geometry, and embracing a more nuanced view that recognizes the importance of those seemingly imperfect features.
Precisely. And this paper, with its deep exploration of smooth approximations and inherent singularities, offers a glimpse into this richer, more textured understanding of geometry. It encourages us to look beyond the smooth and familiar and to appreciate the beauty and complexity that can arise from those points of apparent irregularity.
Now, before we wrap up our deep dive, I want to circle back to a point you made earlier about the potential implications of this work for other fields, even beyond mathematics. You mentioned physics, for example. Can you elaborate on that a bit? Where might these ideas about smooth approximations and singularities find resonance in the physical world?
Yeah, that's a fascinating question, and it highlights the remarkable power of mathematics to transcend disciplinary boundaries and offer insights into seemingly unrelated areas of study. When we think about physics, one area that immediately comes to mind is the study of space-time singularities, like those found at the center of black holes or at the very beginning of the universe, the Big Bang.
So those points in space-time, where our current physical theories break down, where gravity becomes infinitely strong and the very fabric of space-time seems to tear apart.
Exactly. These singularities pose a significant challenge to our understanding of the universe, and physicists have been grappling with them for decades. Now, while the mathematics of general relativity, which describes gravity, is different from the geometric measure theory we've been discussing, there are intriguing parallels.
Are you suggesting that the techniques used to understand and potentially resolve singularities in geometry might offer insights into those space-time singularities that plague our physical theories?
It's certainly a possibility worth exploring. The idea of smooth approximations, for instance, could potentially be applied to space-time, offering a way to model those extreme regions where our current theories fail. It might provide a mathematical framework for smoothing out those singularities in a way that preserves the essential physics while allowing us to make sense of those extreme conditions.
So instead of hitting a wall at those points of singularity, those points where our equations break down, we might be able to use these mathematical techniques to kind of bridge the gap, so to speak, offering a way to extend our understanding beyond those limitations.
Precisely. It's like building a mathematical bridge that allows us to venture into those uncharted territories of space-time, those regions where our current maps no longer apply.
And who knows what we might find on the other side of those bridges? Perhaps new insights into the nature of gravity, the origin of the universe, or even the fundamental structure of space-time itself.
It's a tantalizing prospect, and it highlights the power of mathematics, not just to describe the world as we see it, but to push beyond those limitations, to open up new possibilities, and to guide us into uncharted territories of knowledge.
This deep dive has been an incredible journey, revealing not just the intricate world of integral currents and smooth approximations, but also the potential for these ideas to ripple outwards, influencing our understanding of fields as diverse as physics, cosmology, and perhaps even our philosophical perspective on the nature of reality itself.
It's been a true pleasure exploring these mathematical depths with you, and I hope our listener has gained a newfound appreciation for the beauty, power, and sheer wonder of mathematical exploration.
On that note, we have reached the end of our deep dive. Hopefully you're walking away with a newfound appreciation for the subtle interplay between the smooth and the singular and the vast, intricate world of geometric thought. Keep those brains buzzing, and until next time, happy diving.